only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
I'm talking with Dr. Stephen Wolfram, who's I've known, fortunately for me, for many years. I've been fortunate to receive signed copies of his books. This is one of my favorite books.
Good.
Which is quite an accomplishment because, you know, as a CEO, you know that there's very few CEOs who are very technically or mathematically minded, and getting insight into physicists and mathematicians and thinkers, philosophers from the mind of a CEO and a mathematician, scientist, is quite refreshing. So I actually work hard to learn the craft of leadership, not just the craft of cosmology. So I thank you for this book. I recommend it very highly. Idea Makers. We'll spend a little time talking about that. First, I want to, we'll have, you know, your general bio. I just want to add to my listeners. I have a lot of young listeners out there. I have old listeners, everything in between. We talk about everything on this podcast, from the physics of sports and the Olympics and Krav Maga to business leaders to cosmologists and everything about in between. But this is the first time I've had on somebody who never got a PhD, but I don't think I've ever had someone who didn't get a bachelor's degree. And the person who didn't get a PhD was Freeman Dyson, who I know you know, or knew, the late Freeman Dyson. And the man I'm talking to now is Dr. Stephen Wolfram, but he never got a bachelor's degree. So I was saying to one of my friends, if you put the two of you guys together, you get a really good physicist. I mean, that's... So Stephen, welcome.
Thanks.
So I wanted to ask you a question just to start off. That you've made many contributions to the mechanics, not just the theory and practice of mathematical reasoning, but you've actually introduced technology that has, in my estimation, I mean, tell me if you agree with this, probably performed more calculations than every single abacus and every single slide rule ever invented. Would you agree with that estimate?
Yes, I'm sure that's true. But we have a huge advantage. You know,
yes.
We're dealing with computers that run 1 billion instructions per second.
Yeah.
The guy with the abacus is running at most, you know, an instruction, maybe 2 instructions a second. So we've got a factor of 1 billion advantage right there.
With me, a millihertz. My processor runs about 1 millihertz. And I wanted to kind of start off there because you're today I contacted you because I, like so many of my colleagues, are so excited about this new physics project that Wolfram is involved with and that you pioneered. I want to understand how it came to be, how you were inspired by young people in your life, because we have a mission here to inspire the imagination of young and old. And this particular was kicked off by young people and how it's made its way into the world. But that connection to technology sort of intrigued me when I had that realization that you had completed more calculations by orders of magnitude than any other device invented before the computer, let's say. It made me think, like, what would have happened, you know, had you been born a century earlier? For example, we're born into technology that we have, and there are certain bounds on what technology you can create. And you've proposed this new physics project, but would that have been possible, you know, 30 years earlier or 50 years
right.
earlier? What do you feel about that?
Yeah, I think the answer is basically no, for 2 reasons. First reason is a really practical one, which is, you know, part of how we know what's true is by doing experiments. We can now do computational experiments. That's a fairly new thing. If we'd been a lot smarter than we are, we might have been able to figure out what was true without doing the experiments, but I don't think that's feasible. So the first thing is the practicality of being able to do computer experiments. The second thing is the way of thinking about things that computation has brought to us is something that comes about because we're just used to computation all around us. And that's a sort of paradigmatic advance that I just think is not achievable without sort of a lot of exposure to computation in the wild, so to speak. I mean, I've been very interested in the sort of history of ideas, and some of the things I've discovered are things where I say, gosh, you know, one day we're going to unearth some Babylonian tablet that's going to have one of these things that I've identified. And, you know, they were close. They did some things that weren't, you know, I've studied a lot how simple programs work, how when you have very simple rules, you just keep applying these rules over and over again. You end up not getting simple things out, but you end up getting very complicated things out. And, you know, I've often wondered, could the Babylonians have discovered that? And so I think mechanically the answer is yes. But would they have known what it meant? I think the answer is no.
Right.
And I think that's the, and I know in my own life, the understanding what it means is the much slower thing than the mechanics of being able to do it. But, a lot of the stuff I've been doing now with the physics project couldn't have even done the experiments without having computers. I mean, we're talking, routinely, routine, simple experiment that I might do might involve 100 billion or a trillion operations. I got 100 computers, doesn't take them very long to run that. For me, it's just like, I can just do that on a whim, so to speak. But a trillion operations, there's 12 million stones in the Great Pyramid, for example. That's, now those stones are bigger to lift than my little operations, but it still gives you a sense of scale. A trillion operations is a lot of effort.
Yeah, and to do this, and then naturally, then my mind went to, well, what would happen if Stephen or one of your proteges, your many proteges, came up with it not now but 30 years hence, and it really kind of reminded me a little bit of what Steve Jobs was reputed to have said once. He was asked to give to some philanthropy, to some charity, and he said no, and his reason was he could take money now and invest that money much better than the charity could, and then at the end of his life, which unfortunately was not very long, he would then donate a much larger sum. So he sort of proclaimed this, the virtue of sloth, if I recall correctly. And I wonder, with the advent of quantum computers, and I haven't read, apologies if you have discussed this, I'm trying to keep up to date with all your output, but what the bearing of quantum computing could have on it. I know there are packages, and we'll talk about Wolfram language and so forth. But what about, had this not come for 30 years, do you think in the net aggregate that physics would be delayed or forestalled by some amount?
Yeah, so I mean, well, by the way, about quantum computers, one of the implications of this theory of physics is it gives us kind of a new, cleaner way to think about quantum computing, both what it can do and what it cannot do. So I think that story is about to have some slightly different turns in it. So I wouldn't hold out the hope for, and the fact is computers get faster only rather slowly these days. Right. But in terms of, when do things happen, and when is the right time and so on, I've been lucky in that I've lived in a period of history where something which is really interesting to me and which I'm maybe even quite suitable to doing, which is studying computation, has just been sort of coming online. And I do think, I always think about people in general. I always have this theory that for every person, there's sort of the ideal niche. And the question is, does that niche exist at this time in history? And, what I see when I've been involved in introducing a number of sorts of ideas that end up getting lots of people involved in working on them and so on. And what I see is that when one of these new ideas comes out, and we're seeing that now with the physics project, there'll be a group of people for whom these ideas will really resonate with the things that they're interested in. Those people may be young, they may be not so young. And it's like, well, we lucked out because, at some point during their career, something came up that really resonated with what they're interested in, and then they can go off and really make a success of it. And I think, if you live at the current time and the thing that you really want to do is, explore the source of unexplored rivers, well, you're out of luck because all the sources of all the rivers on the earth are known. If you want to, there are different things that become possible at different times in history. And, as I say, I've been lucky that this thing of computation kind of during my lifetime has gone from something very kind of embryonic to something that is at least better developed. I think we're far from all the way through, but so I've been kind of fortunate. I was observing a lot of what I do in sort of the raw material of the work I do is computer experiments. What do all these simple programs actually do? And I think I even wrote in some recent post of mine, if I had lived in a different century, I think I would have been a zoologist, because here I am looking at all these weird things that these programs do and trying to classify them, trying to understand what they are. Now, truth is, I'm a really squeamish person, so I don't think I would have made it as a zoologist, but that would have been at least my potential interest, so to speak. But yeah, no, it's I mean, this question about when are ideas ready to happen in the world, it's a really interesting question. So, one of the things that I think is sort of the most interesting, probably the most interesting single discovery I've made I made in the 80s, is this phenomenon that even really simple programs, so you know, when you think of a program, you usually think of something you write explicitly for some purpose. But you can also imagine sort of the more scientific question, just like pick a program at random, tiny little program, a program that's just a line long, just a few rules for what it does, and say, what does it do? And you might have thought, as I did, oh, it'll only do really simple things. But it turns out that isn't true. It turns out that, you know, even this really simple program can do really complicated things. And that, for me, was sort of a big sort of intuition breaking moment when I realized that. Now, it's also worth saying, when I actually discovered that, it's a little bit embarrassing, but, you know, I first did those experiments probably in 1981. Okay, I did the experiments where I had, you know, these printouts. I even published them in a paper with these printouts with, you know, all these things where I got very complicated behavior with very simple initial conditions, et cetera, et cetera, et cetera. But I mostly focused on another aspect of what was going on. Mostly focused on something about how order was created, not how this sort of randomness was created. It took me 3 more years to realize that this thing that was actually right in front of me was something really important. And then I kind of realized, you know, well, haven't people seen this phenomenon before? And I realized, well, actually, you know, when you look at like the digits of pi, they're very simple to specify. Yet once you generate those digits, they seem for practical purposes, you know, people remember 3.14159, et cetera, et cetera, et cetera. It's kind of a game to see how many you can remember. And it's hard to remember them because they're kind of random.
Yeah. I use the middle 4 digits as my PIN number of pi.
So you shouldn't tell people that. The middle, yes. You can go any distance to get to the middle. Yeah, we had a thing actually on the pi day of the century. We had a thing where you could type in your birthday and it would show you where in pi your birthday appeared.
Oh, wow.
So you didn't get any information there. So
That's right.
Good stuff. No
That's
computer security.
That's right. No hacks possible. Yes.
But no, you know, I think what happened there is something like, you know, digits of pi. There is this randomness that one saw there, but nobody really cared. It was just like, that's random. We can't say anything about it. Mm-hmm. Same with primes. People were, you know, the distribution of primes, which numbers, you know, 2, 3, 5, 7, 11, et cetera, et cetera, et cetera, that which numbers are prime, plot them out. It's kind of random in some ways. There's a certain density of them, but otherwise there's sort of random fluctuations. So there's endless mathematics done on the distribution of primes, looking for the regularities in the distribution of primes.
Right. Prime pairs. Mm-hmm.
Yeah, right. And all sorts of, you know, what's the density of primes? That's the prime number theorem. You know, the Riemann hypothesis is all about certain aspects of the density of primes and so on. A lot of famous, well-known mathematics about the regularities in the distribution of primes. But actually, one of the most striking things about the distribution of primes is the apparent randomness of the distribution of primes. And, you know, before the kinds of things that I've done, nobody cared about that. I mean, it was so, you know, what you find, and I find it really interesting, actually, that there are these phenomena that the phenomenon is there, but nobody cares. Mm-hmm. You have to have a sort of paradigm wrapped around it to make people want to care. And it's, you know, I think for me personally, that's been the main limiting factor in progress, is getting to the point where I have enough sort of ambient understanding that I can see what the questions should be and see why one can care about the phenomena one's seeing.
Yeah. And I wonder, you know, just going back in your history, and people, you know, can certainly read about it in all sorts of places, and we'll put links to your biography. I don't like spending too much time with people that, you know, asking questions that almost anybody can research, even on WolframAlpha itself. I want to just ask you, though, something that is a commonality in all your work since I started following you in the 90s. My father, you know, was one of the main reasons that we could talk to each other, is because I could actually program in Mathematica in the 90s, and he was interested in proving some new theorems in quantum mechanics and relativity and things in his later years. But I wondered, you know, as we would go through it, the sort of thing that always appealed to me, even before you came out with sort of this notion, overarching languages, that you're really kind of a linguist in a sense, that these different natural language or algorithmic bases for language, and we're certainly going to get into more of that in a moment. But would you say it's accurate that sort of you have this, if you were to reduce the irreducible complexity of you were just talking about the irreducible complexity of pi, at its core, would you find, you know, the prime numbers of Stephen Wolfram have to do with fascination with language and coding and algorithms?
I don't know. Because I'm one of these people who's been involved in, well, finding, managing lots of talented people, and I kind of try to understand sort of how to get the best things out of people and oneself. One of the things that's sort of an exercise for me is, what am I actually good at doing? And I've done a lot of different projects that in science and technology and so on. And I sort of realized at some point they are actually all the same project at some level. And the way the project works is, the subject matter is different. It's physics, it's computational knowledge, it's, computational language design, it's things about the computational universe of programs and so on. But basically the pattern of my projects, and they're often very long projects, tends to be there's some big complicated thing out there. I then try and sort of drill down and figure out what are the sort of underlying essential primitives. And then, having got those underlying essential primitives, then try and build the whole thing up again as a sort of piece of engineering to actually make something that is sort of a big story, a piece of technology that's useful or whatever else. Now, in doing that, one of the things that certainly comes up is when you break things down to those sort of underlying primitives, what are they and how do you describe them? And, I've spent some significant part of my life as a computational language designer. And what that means, it's sort of the opposite of what a linguist does. A linguist says, we've got these languages that all these humans speak. What are they made of? How do they come to be? And that's much more of that tends to be much more of a kind of sort of a what did we get thrown by this apparent historical accident of linguistic evolution? Whereas what I've been interested in doing, although it's not quite as far away as it might at first seem, is to take what are the set of things that are sort of possible with computation, and then figure out how do we describe those with a language. So what does it mean to describe it with a language? What one's really doing there is there's this whole ocean of sort of what's possible to do computationally. And then there's the parts of that we humans actually care about. You can run an infinite set of possible programs. Many of them will do things that if you were to make a living studying them, you would say, oh, that's really interesting. But without a context for them, it's like, why do we care? There's a certain set of things that we humans have decided we care about. And the role of a computational language designer is to kind of make this bridge between the things that we humans think we care about at a particular time in history and the things that can be done computationally. So it's like, for example, the thing we might be doing, right now, a podcast, right? There wasn't a word for that thing 20 years ago.
Right.
And yet, so we see this sort of circular process. There's this sort of thing that eventually happens in the world. Eventually, it makes sense to kind of describe it in some sort of symbolic way of, oh, that's a podcast. And what's funny about the way that human, sort of civilization evolves is once you have this way to describe it, it's much easier to have more of it, so to speak. Because people know, you ask me, do you want to be on this podcast? I know what you're talking about. Right? Whereas, otherwise it would be this long, complicated description. So in some sense, this process, I see my, a large part of what I do is sort of this interface between what we humans kind of understand and are interested in and what's possible at a computational level. Actually, that's one of the things that's kind of interesting to me about this physics project, is that to me, in some ways, this is the ultimate language design problem. Because, what do we have going on? We say, what is the universe going to do? Well, we don't really need to have a theory for that. We can just watch the universe, see what it does. On the other hand, we have, we have this kind of, the goal of a theory of physics is to have something where we humans can sort of tell a story about how the universe works. The universe does whatever it does, but can we reduce that to something which we can tell a story about, so to speak?
That is computable. That's right. Yeah. So speaking of, languages and creation, I want to first take a little step back before we get into the nuts and bolts of the physics project, back to some exposure that all of our listeners, since we are named after the Arthur C. Clarke legacy, the Arthur C. Clarke Center for Human Imagination, And the podcast name itself is Into the Impossible, which derives from Sir Arthur C. Clarke's second law, which is the only way to find out what's possible is to venture out a little bit into the impossible. And that's where we get that name. Of course, the first law of Arthur C. Clarke also applies to you in many cases, because it's essentially a statement about technology, that any sufficiently advanced technology is indistinguishable from magic. Later, I do want to get to, just as a teaser for folks that are listening, to hopefully enjoy the entirety of the podcast, because I do want to, maybe tickle your brain a little bit and talk about some of the philosophical or maybe perhaps even theological implications of creating magical technology, as Sir Arthur C. Clarke would say. And I want to pick your brain about that. But first, I want to take a step back to perhaps, I think you're known in the popular culture, for many things, but one thing that I think you're known for, particularly is, well, besides the fact that you're in, roughly half the pockets of people in the world in terms of Siri, and I'm probably setting off some smart assistants around the world by mentioning this, but WolframAlpha powers so many of the different search queries that Siri will actually execute. And I do want to point out, I'm in the show notes, I'm going to have some links to WolframAlpha, and have some exercises for kids and adults even to play around with, to get a feeling for how the symbolic computation may work. It's such a powerful app, compared to what you might just be using on your, I now have gotten to just, yelling out into the ether to my smart assistant to do some calculation, but it's so much more fun and viscerally, associative when you do it on something like WolframAlpha. So we'll talk about that. That's one area of the zeitgeist that you're deeply enmeshed with. The other one is your role and your son Christopher's role in the movie Arrival, where you were tasked with something that is just delightfully mercurial, and knowing you, that's your signature trademark, of creating a language. The two of you have created sort of a language that was used in the film. I do want to point out that the story of your life, which was written by Ted Chiang, we had one of the world premieres of it with him back in 2016 here as part of the Arthur C. Clarke Center. I'll put a link to that also in the show notes so people can watch that video with Ted and members of the Arthur C. Clarke Center. But I want to talk about this Arrival story, because I think in a lot of ways, I often think about, how would you communicate? What are some universal, communications that you can have? And I gave a talk once at the SETI Institute in which I invoked your former friend and mentor, Richard Feynman, where he talked about if you ever met an alien and he or she or it or she or whatever sticks out its left hand to shake your hand, don't do it, because it's probably made of antimatter, and therefore you'd be annihilated, he said. So this is in his Feynman lectures on physics, which you might have actually taken as a graduate student, perhaps, or certainly known about them. But
I read them when I was a kid, actually.
Yeah. So wondering whether or not how you would communicate symbolically. In the talk I gave at the SETI Institute, I pointed out, perhaps you could use the cosmic microwave background, its patterns, as a way to distinguish, in Feynman's question, how do you tell them that the heart of a human being is located on its left side? Well, the first thing they're going to say is, what's your left? What does that even mean? And I wonder, in the construction of that talk that I gave, how would you do it? And for you to come up with this language, can you walk us through that exercise and what it was like, and why, of all things to spend your time on, you did get so deeply invested in that wonderful movie?
Well, the movie thing was a lucky thing, because it was one of these. I think movies are a very high noise activity. That is, there's a lot of things people talk about doing, and a small fraction of them actually get done. This was a case where we were sort of fortunate enough to get involved with that movie right when it was about to start filming, and when it was for certain that something was going to happen. And it's also was very much a tribute to the director, that the movie came out as well as it did, because when I first read the screenplay, it was like, oh my gosh, how are you going to make, it's a very interesting but very complicated story. What are you going to do with it? But this whole problem of how do you communicate beyond the sort of our existing culture, I've thought quite a bit about this. I actually wrote a piece about that. I got involved. A friend of mine has a thing called the Arch mission, whose goal is to put artifacts from our civilization out into the solar system as sort of beacons of, this is what those humans achieved if the extraterrestrials come through long after we're extinct. Okay, and so one of the dramas last year, actually, there was some stuff that these guys had got put on the Israeli moonlander.
Yes,
and, that was so. I was kind of watching. What's going to happen with the Israeli moonlander? It's really a cool mission, and at the end, it's oh gosh, the thing crashed into the moon at 2,500 miles an hour.
Yeah, still a better driver than some of my Israeli friends. Just kidding out there. I'm not, nothing.
Well, let me
negative.
tell you something about that, though. We figured out. So, I was curious, did the payload survive?
Yeah.
Right?
Yeah.
And so initially I thought, no way, 2,500 miles an hour, it's not a chance. But it turns out I got in touch with a person who's sort of a world expert in cratering. And one of the things that was interesting was that spacecraft impacted the moon at, I forget what it was, maybe a 15-degree angle, maybe less than that even, a very grazing angle. It didn't deorbit correctly. That was kind of what went wrong. And so, I was told, well, actually, at that angle, the thing doesn't just go splat, it bounces. And in fact, we then got some footage from the Lunar Reconnaissance Orbiter, and you can see there's this little ray that shoots out, and we calculated where the thing had been and so on, which was a little bit tricky because there's no GPS for the moon, right? So you have to take the photographs and you have to match them up with craters and things like this. Well, anyway, there's a ray going out from the impact site right at the correct angle. So I'm pretty sure the payload actually survived. So on the moon, there is something which I don't think is going to work for the extraterrestrials, but it was an attempt. And so the question is, what can you put there? Yes. What is the sign that tells them something interesting about our civilization? I think in the end, this is a philosophically doomed project. Okay, so in other words, we can start thinking about what do you do. So for instance, let's imagine we're a really advanced civilization and we can move stars around. Okay, and we want to put a sign in the galaxy saying we're really smart over here.
Einstein lived here, right? Einstein lived here, right?
Yeah, right. What configuration of stars do we put in there? Okay, well, you might say, well, let's put them in a perfect geometrical figure. Okay, bad idea, because there's lots of physics that leads to perfect geometrical figures. So that's not an immediately. You might say, like pulsars, for example. When they were first detected in 1967, I guess. People were like, for the first couple of weeks, they were like, there's a radio signal. It's going beep, 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 periodically. That must be an extraterrestrial beacon.
Yeah. Well,
actually, no, it's just a rotating neutron star. And, the periodic thing just isn't something sort of sophisticated enough that you can know, oh, that couldn't just be a simple physical process.
Right. Or a maser. We have maser examples in space, and
absolutely.
We have them here on Earth. So it's not a sign of intelligence. Yeah.
Right.
Yeah, go on.
So, I mean, the challenge is, what do you find? And actually, one of the nice stories from the past is back around 120 years ago or something, when radio was new. Okay, so there was Marconi, there was Tesla. These were people who were working on radio, and Marconi observed. He had this yacht. He went across. He was a good business person and had got a yacht that he went across the Atlantic in, and in the middle of the Atlantic, with his radio mast, he heard all these weird whooshing sounds and so on. It's like, what on earth is this? Tesla was a little bit more forward in his theory making, and he said, look, it's got to be the Martians signaling us. I mean, what else could possibly have radio? Radio must be a sign of the Martians, so to speak.
Right.
And then what is it in fact? It's features of the ionosphere. It's kind of
whistlers.
Right.
Yeah.
And but then the thing that's really the confusing thing for me is, listen to whale song recordings. They sound awfully like that.
Yeah.
In other words, you got this thing that's produced by the ionosphere that's just a physical process. You got this thing that's made by whales that at some level is a physical process happening in the brains of the whales. But we think it has more meaning than that, probably, although we don't really know for sure.
Yeah.
And so you quickly realize this is a difficult problem. And, we look at archaeological artifacts. We say, what was Stonehenge for? Well, we're not quite sure. What were these things? You find some flint that was, seemed to be chipped off. Was that done on purpose to make an arrowhead? The way that we get to know whether these things were sort of on purpose is when there's a kind of thread of intentionality between those things and us. So, for example, if we recognize, oh, that was a thing, I remember I was visiting some archaeological site in Peru recently, and a very interesting site. It's one of the earliest kind of settlement type things in the Americas. So going around, and that's the stone thing, and there are a bunch of different structures, and the person it's a very isolated site, so there weren't a lot of tourists there. But the person we had showing us around said, "What's that for?" I said, "Well, that was for ceremonial purposes." And so, you quickly learn ceremonial purposes.
The brochure that said, the marriage.
We have no idea what this was for. And, I'm thinking about things that exist in today's world. That shopping mall was for ceremonial purposes. So it's like, how do you tell, how do you connect? When we have a certain cultural experience, we can connect that sort of thread of purpose, or that sort of spark of this was done on purpose, to something that we see in the world. When we don't have that connection, it's really hard.
Yeah.
And I mean, in the case of sort of the extraterrestrial case, it's I think it is not something you can ever count on really being there. And I think the way to think about that is, my statement in recent years has been, when you think about intelligence, I don't think there's sort of a bright line between the intelligent and the merely computational, so to speak. So, people say things like, the weather has a mind of its own. The weather seems to do things that are very hard for us to predict. It seems to have, it seems to sort of decide what to do itself. Okay, does the weather have a purpose? We don't think so. But, I'm not sure. Maybe the purpose of the weather is to transport, hot air to this part of the world, and transport cold air to this part, and so on. But it's really hard for us to say, and then to say, well, the sort of the process of the weather doing its thing is an exercise of computation that, at least based on basically a bunch of science I've done, is sort of no more or less sophisticated than the kinds of computations that go on in our brains.
Yeah.
So it's kind of like that we're saying there's a computation here, it's equivalent to the computation there. We say we care more about the computation going on in our brain because it seems to have meaning to us. The weather doesn't seem to have meaning to us because it doesn't have this connection in the way that sort of other brains do. So, I mean, I think that's the, and so when you sort of extend that to the rest of the universe, it's like, does that pulsar magnetosphere have a meaning or not? Very hard to say.
Right.
Now, the thing I have tended to think is that our first example of alien intelligence that we sort of understand is rapidly emerging in the form of artificial intelligence. I mean, when we see an AI, we know we made it. It's a program that we created, but we say, what's it doing? Is it doing something, and how do we think about what it's doing? How do we think about what it's thinking about, so to speak?
Right.
We open it up. It looks like it might be an EEG recording from a human brain. It looks complicated and random. And we, while we know how we constructed it, we don't know we don't have a narrative that explains why it does what it does, any more so than we have a narrative that explains why our brains do what they do in detail. And so I think my basic statement is people will stop worrying about extraterrestrial intelligence once they really understand AI, because they'll realize that things out there are intelligent in the sense that they have this computational capability that's just like us.
Right.
This question of whether they have an alignment of meaning is a deeply detailed historical question that isn't an abstract question. It's not like you say, is the pulsar magnetosphere intelligent? Is it a civilization? Did it grow up over large amounts of time? Who's to say? It's like looking at. One of the things that's come out of this physics project of mine recently is I always said, and when I was working on that ArrivalMovie, one of the things I sort of said was that, well, at least any extraterrestrial intelligence has the same physics that we do. It lives in the same universe.
Dimensions, yeah.
Right. And it's like, but I don't think it's true, because what I've realized is that that, and this is sort of a sophisticated point comes from the physics project, that there are these kinds of ways of understanding the physical world, which are, in some sense, it's the same physical world, but they are deeply incoherent ways of understanding it. So, for example, our understanding of the world is sort of based on our senses. We see, we detect light, we do this, we do that. And, there are little details. Like, for example, for us, we look out in the world, most of the things that, because the speed of light is really fast compared to the speed of our brains,
right?
What we see out there in the world happened, immediately, so to speak. It's not the case that.
But if we perceive primarily through sound, we would have a very different description of relativity. In fact, my late father, wrote a paper about relativity for bats. I mean, bats are getting a lot of bad press these days. But yeah, communicating with echolocation, and so they might have a different series of Lorentz invariant type objects.
I'm gonna have to look that up.
I'll send you a link to it. Yeah, it's from the 70s. But yes, you're right. It's sort of a reflection of our own prejudices, how we write down the laws of physics. So is that what you're getting at? That aliens might have different perceptions, like the ones in Arrival, and therefore their laws of physics might be revealing something totally different, and that we are completely blind to.
Yeah. I mean, I think it's one of that's the most extreme case. I mean, the first issue is, even when it's the same physical processes, even when we're noticing the same things, we're seeing light, we're seeing other things, even then, connecting meaning seems essentially impossible. But even going beyond that, when we're asking, is it really the same physics? Are we sensing? Actually, I think the more extreme case than bats that I've been curious about is dogs, because they, olfaction, smell, is a key thing for them, and the speed of olfaction is really slow.
Yeah.
I mean, it's the speed of diffusion of molecules in air, and that's so for that, the dog is walking. Is definitive, for a bat is flying slower than the speed of sound, but a dog is walking faster than the speed of olfaction. And so its view of things like relativity will be even more bizarrely different. Now, there are, it isn't the case, the sort of constancy of the speed of light that happens in physical universe, it doesn't quite work the same way for olfaction or for sound,
right?
Because there's actually an ether, so to speak.
I think I know what you should call this. I think you should call it the theory of smellativity. I couldn't resist. Yes, I'm sorry, Stephen. Go on.
Yeah, no. I mean, I think that, the thing that has been, I think, one of the surprises from this physics work that I've done recently is this realization that, again, this is a slightly complicated thing, and I'm sort of skipping way ahead.
Yeah.
Let's not skip ahead. We'll
get to it. Yes, I do want to get to that. Yeah, and I think the exercise in kind of constructing these virtual worlds, and that's something that we do here at the Arthur C. Clarke Center. We don't construct them, but we envision them. What will San Diego look like in 50 years? How will we be communicating? What will be the fundamental, irreducible aspect that leads to future life being better than present life? And I think, obviously, for us, that cleaves towards this notion of creativity and imagination. And I wonder to what extent you were influenced by science fiction. I know you've had an influence on science fiction. Our namesake, Arthur C. Clarke, of course, he was influential in both science nonfiction and science fiction. And sort of this perception that we come to is that from talking with colleagues such as Dr. David Brin and even Michael Shermer, who was on the podcast recently, that science fiction represents sort of a way to pregame, to sort of think about the future as a Gedanken experiment and play around with it, and maybe not with the hopes of, really coming up with, well, what's the first, message that we send to the aliens that when they arrive, but more how we understand ourselves better. And I wonder if say working on Arrival, did it have any beneficial, I mean, just as a shortcut, did it make it anyway into the physics project? Just out of curiosity.
Okay, that's an amusing question. I mean, so just to mention, I actually wrote recently a long post about 2001: A Space Odyssey, because it was the 50th anniversary.
I'll have to post a link to it. Yeah,
right. I realized it was the first movie that I had ever seen in a movie theater, and it turns out it was because I saw it in England when it was kind of just first out. They were handing out these programs in the movie theater. And because I'm a kind of archivist pack rat, I had the program that I'd been given when I was like 8 years old or something at this movie. So that was kind of fun. But it was interesting to go back and look at 2001. I really liked that movie. It was a very kind of bright view of the future, and I think it was in many ways quite influential to me in terms of sort of this concept of what the future might be like. I was kind of amused going back to look at it and seeing the things that were got right, the things that were got wrong, the things where the HAL computer that's in 2001, the kind of intelligent computer, in many ways, the things I've built in kind of practical AI are kind of, they're in a sense an embodiment of the practical version of HAL, and I'm sort of been interested in that. I think it was amusing to me that I'll tell you one funny thing about many funny things I discovered about that movie when I went back to look at it again. But every so often there's a screen that flashes up where it has code, like computer code. It was actually IBM was the main organization that consulted on that movie. Although
that's HAL, right? That's where HAL.
Yeah.
Comes from, right?
Well, that may have been a coincidence, may not have been a coincidence. I'll tell you one thing I discovered when I was writing the blog post about this is that for IBM they were very freaked out by the idea of an intelligent computer that could that could sort of not delight the customers, so to speak. I think it would be fair to say that in 2001, without being too much of a spoiler for the movie, that the computer did not delight its customers.
Surprise and delight, as Steve Jobs would say.
Yeah, right. So IBM was very freaked out by that vision of computers. So they really wanted to distance themselves as much as possible. So it was in the movie. It was called the HAL 9000 computer, and IBM did not have a computer whose number designation started with a 9 for, I think, 35 years after that movie came out. So that was the
it's a consequence of
yeah, right. But no, I think that in terms of science fiction, I'm not a big reader of fiction, actually. Mm-hmm. So to my detriment, probably. I mean, I think it's fiction is in many ways a way of communicating things more effectively than probably just writing down the facts. But I'm probably too impatient a reader to deal with that. But I think, this whole question of when do you get to imagine things in science fiction versus how do they come out in practice? When I was working on this stuff about communicating with future civilizations and so on, and kind of leaving beacons from our civilization, I figured out a bunch of things that have a very science fiction feel to them. And so I thought, I sent this off to some friends of mine who are science fiction writers, and one of them was like, I could write an interesting story about this, and started to outline the story. And I was like, well, that story just has a lot of fluff around it. I just want to get to the main point. So I thought, I'll sit down for an evening and I will write a science fiction story. And I realized I haven't written a fiction story since I was a kid. And I write this thing and I send it off to my friends who are science fiction writers, and they say, just stick to the stuff you usually do. But it's funny because I find that, in terms of the communication of fiction, I've done quite a lot of historical biography and so on. And for me, I find it very easy to write about people and about people I've known and things like that. But when I have to make up a person who I've never known, somehow that's a different thing. And somehow I feel like, if I say, well, it's just this person I'm writing about, I probably could do that. But when it's something that comes from inside me, it feels too revealing of anything about me to be able to, sort of make up the person, so to speak.
So there's too much influence from the author, so to speak. And maybe maybe we'll, go ahead.
But no, I mean, in terms of the future and so on, I think one of the things that, I've been very interested to understand what are the kind of, what are the conceptual things that are shaping the future beyond the kind of, one of the things that's come out of this physics project, for example, is, the physics project, I think, is giving really very good evidence that our universe is at its core computational.
Mm-hmm.
And what does that
Can you take a step back, Stephen? Can you explain for the audience who may not be familiar, what does it mean to be computational? And, for example, the difference between complexity that we've talked about, irreducible complexity, something like pi, where the description of the thing is the shortest possible description of the thing.
Actually, it isn't.
Okay.
See, pi is an example of something where the description is very short, but the thing you get out is very complicated. But so, I mean, just to say something about sort of what is computation,
yes.
What do we mean by that? Essentially, all it is you have rules for how something works, and you just keep following those rules. So, for example, one thing I've studied a lot are things called cellular automata. Fancy name, simple idea, just a line of black and white cells, and there's just a rule that says if you have a black cell with a white cell and a black cell, for example, then you get a black cell at the next step, or all the different configurations. It tells you there's a rule. It just tells you what happens at the next step. So it's a really simple set of rules, and you're just applying those rules over and over again. And ultimately, that's what a practical computer does as well. It has rules that say how its CPU should work, and it's just applying those rules over and over again.
So having something like your beloved and famous Rule 30, what is the computer? Is it the rule that generated this magnificent complex pattern? Is it the pattern itself? I mean, if I go to, the cashier and I say, how much is it? And she hands me Rule 30, there's nothing I can do with that. It's beautiful to look at, but perhaps, I mean, what the computation is, where is it occurring? In the physics project, is it occurring in the mind? Is it the universe? Can you explain for listeners, where does it occur?
Yeah, right. So, I mean, it's a little bit of a tricky philosophical issue, because you're saying, I have this rule, it says this and this and this happen. Okay? That's what theories are. That's what any theory is. When somebody had when Newton, for example, had his theory for how planets move, that was something where he wrote down a mathematical equation. He says, solve this mathematical equation and you will know how planets move. So there is a sort of the mathematical equation itself has some abstract existence, and it generates numbers or whatever else. But that is merely a description of what the planets are doing. It is not that the planets are mechanically having, a thing that's working out numbers inside them.
As Maxwell thought.
Right. Yeah, it's just that's a description of what's going on. So similarly, in the case of something like Rule 30, we have a rule that's a description of what should happen. We may implement that rule on a computer. That may be the way that we happen to see the results of that rule. Now, the case that's trickier is for the whole universe, because we now have, I think, really very good evidence that the universe operates in a computational way, that there is an underlying rule, and that rule has been applied trillion. I need to be more practiced at counting the trillions.
To the
times.
80th, right?
That rule, after it's applied as many times as we need to, makes us and makes the conversation we're having and everything. And that idea. So the idea is there's a fixed rule, and it's just getting applied over and over again. Now you say, well, what's running that rule? Well, what's running that rule is the universe. That's a description of what the universe does. We could try and have a computer emulate that rule. We wouldn't, the universe has been running a long time and it runs really fast. So we wouldn't get that far doing it on our, laptop or whatever, but we might get to, 10 to the minus 200 seconds in the history of the very, 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 trillionth of a second in the evolution of the universe, on our, by emulating that rule on our laptop. But the universe itself, what we're saying is we can describe what the universe is doing as it's following this rule that we can think of as being a rule that could be run on a computer.
Is it because, and we should take a very brief side detour. I don't want to get too deep into it. There are some who literally believe that the universe is being run on a computer of sufficiently advanced AI, or, it might even be it might even be artificial. And that, could you just comment? I've seen a lot on the internet, people speculating that this is somehow connected to, this matrix or this ultimate simulation.
Yeah.
Could you just say, just dismiss or confirm?
It's a philosophically doomed idea. That is, here's what happens. So, if I'm right that basically the universe is operating according to some computational rule, then at some level, in the end, there's just this computational rule that's running the universe. So now we ask ourselves the question, and it comes back to what we were talking about before. We've got this rule. We can hold it in our hand. We can show it. Here's the rule for the universe. Now we say, was that running inside somebody else's computer? Was that a simulation being run inside somebody else's computer? First question is, there are two levels of doom for this idea. The first question is, what does it even mean? We've got this rule that runs the universe. Now, you've got to then argue, was this rule created for a purpose, with a meaning, by a game designer, a universe designer? Or is this rule just a thing? And that comes back to our question of sort of, in the case of human archaeology, do we know whether Stonehenge was created for a purpose? Even that's difficult. Mm-hmm. When we've got this little tiny rule and it generates our whole universe, and we say, was this created for a purpose? Tough question. Mm-hmm. Now, it's even worse than that. That's the first level of doom for that idea. The second mm-hmm. level, something a little bit more abstract, that comes out of this physics project I was sort of alluding to earlier. So one of the things that's very strange about this physics project is the following thing. If we believe there's a rule that runs the whole universe, we can imagine the day when we actually have that rule. And let's say it's fairly simple, okay? It's a very weird feeling because we're saying, for the last 500 years, we've basically been taught over and over again, there's nothing special about us. Right. From Copernicus on, it's like the Earth is not the center of the universe. There's nothing special about
the center of the galaxy, right? Mm-hmm. Our galaxy is not special.
Right. Mm-hmm. It's just like there's nothing special about us. Okay, so now we decode the whole universe. We get the rule for the universe, and oh my gosh, it's a very simple rule. That's very special. How could we have got universe number 3216 as opposed to universe number quintillion, whatever? Mm. How come the rule for our universe is that simple? Okay, so I've been really, really sort of thinking about that question for ages. How could this possibly be the way it works? But what would it even mean? What is the philosophical, theological implication, scientific implication of here's the rule and it's simple? And what I finally realized just very recently, actually, is the following extremely strange fact. So if you imagine there's a universe that's operating according to a certain rule, and then you imagine another universe operating according to some other rule, but then you imagine the entities within those universes, which are themselves operating according to the rule of that universe. So the observer of the universe has the same rule as the universe itself. Well, there's a thing that we're calling rule-space relativity or ruleo relativity, which is basically the statement. So in relativity theory, one of the things actually it's older than relativity, Galilean invariance, the idea that if you're in motion, you still perceive things to work the same way as if you're at rest.
Yes.
That's kind of a fundamental equivalence principle in physics. Mm-hmm. So similarly, it turns out that there seems to be a rule-space relativity, which means that independent of what rule you're using to describe the universe, if that same rule describes you perceive the same facts about the universe. So so what that means is that, in a sense, when we say the rules of the universe are this and that, we are picking a certain reference frame with which we're describing the universe.
Yes.
And that just like so that reference frame, just like we say, we're staying still reference frame, or we're in the reference frame going at 100 miles an hour, or at half the speed of light or something. These are all, we know from relativity that those will all sort of perceive the same behavior. So similarly, what turns out to be the case, and it's a very bizarre thing, these reference frames that have different description languages and that have different, that sort of imply different rules for the universe, you can change your description language, change your rule, it'll all work out the same. So to the entity within the universe, it all works out the same. So the only thing that you end up realizing is that, okay, so this is the simulation argument. So turns out this game designer of the universe could be super lazy because any rule they pick will end up with the same result. So that's kind of a pretty big downer. If your first question is, you've picked a particular rule, why that rule, why not another? Well, it turns out that the rule that you end up picking is, in a bizarre way, a reflection of our way of describing the universe. That is, with our particular senses and our particular ways of doing mathematics and so on, we have created a certain way to describe the universe. And in terms of that way to describe the universe, we can have, we say the universe operates according to a certain rule. And that's, in a sense, what we're trying to do in my physics project, for example, is to find the rule that matches with existing physics. So find the rule that with the description language that we have used for physics is the thing that explains how the universe works. But in terms of the simulation argument, this is sort of the ultimate doom for that argument is that in the end, it doesn't matter what rule you pick. So if a different rule had been picked, we still, in other words, all those rules are equivalent. The universe could be running all those rules at the same time. It doesn't make any difference. For purposes of the entities within the system, they can have a variety of different description languages. Each of those description languages corresponds to some particular rule. So it's a little bit complicated. I mean, I would consider this kind of the sort of almost a high point of kind of the levels of abstract understanding of both the science and the philosophy of what's going on. But I think in the end that makes it the designer of the universe could do basically nothing. They just have to say, now the part I don't know, and I have to say not without thinking about it, is just because you have an abstract description, what makes it actualized? What makes it actually happen? And that we don't know. I have an idea about that, which is very bizarre and abstract. But okay, my idea about that is more or less the following. And this may not be right because this is the new last week's idea. So so in mathematics, there is this thing called Gödel's theorem, and Gödel's theorem says you can have some set of axioms that try to describe mathematics, and you can end up with statements, mathematical statements, which those axioms can neither prove nor disprove. So actually, I've been long on the hunt for really simple mathematical statements where the standard axioms of mathematics just can't reach those statements. There's no finite proof that the statement is true or not true. That's Gödel's theorem that says that can happen. Okay, so Gödel had a second incompleteness theorem that said that from within a system, from within an axiomatic system, the system cannot establish its own consistency. So in other words, you've got this set of axioms, and it's like, are these really right? Are they inconsistent? Within that system, one of the statements you cannot prove is the consistency of that system itself. So I have this vague thought that for an entity embedded in a universe, there may be a similar undecidability result that basically says you'll never be able to answer the question of essentially why the universe has been actualized. And although I haven't managed to get that completely crisp yet,
right?
That's kind of my best thinking so far about how that might work.
One thing that this highlights for me. So if you're entitled, and you certainly are as my guest, to veer into some speculation, I want to run this speculation by you, which is that, in my opinion, physicists like myself have sort of a mathematician envy in that we don't have the equivalent of a Gödel hypothesis. We don't have a way of describing not what is physics, but what is not physics. At least as close as we typically come, and this is controversial, is Popper's sort of dialectic, the distinction between demarcation between what is falsifiable and what is not falsifiable as being sort of appropriate fodder for consideration by a self-respecting physicist such as myself or yourself. I think that physicists, as I said, have envy of mathematicians because that's not accepted by everybody. In fact, I point out that Popper, as you well know, his original, topics for discussing discussing falsification were astrology, Marxist, socialist ideals, and so forth. And I say in my book, that all you have to do is look at the horoscope column of your local newspaper, and you'll see that astrology is alive and well despite being falsified. So it can't be that there's something fundamental about Popper. So what is the equivalent, or is there an equivalent to say that yes, this is physics, what you are doing is physics, and then if not, and we'll come back to this if there's a long explanation, but if it's not true, is there something that you in the physics project can produce that is falsifiable, or is it something, and this is asked by one of my listeners on Twitter, he asked me to ask you that, and I think it's a legitimate question. So first of all, what do you think about this notion that we lack this equivalent of Gödel for physics?
Okay, you have packed many different ideas into here, some of which I have thought about for many years. So let me try and unpack a few of these things. Okay, so let's start off with one that's really easy. The analog of Gödel's theorem for physics. Mm-hmm. That one is easy. And it's something I first started talking about in the early 1980s. It's computational irreducibility. It's this phenomenon that you can have a system where the actual behavior of the system corresponds to a computation that you can't get ahead of. So one of the things that was a big surprise that at first was kind of a footnote, actually. In Gödel's paper, actually, it was a footnote. It got a little bit more prominent with Turing's 1936 Turing machine paper and so on. This idea that, okay, so one thing you might think is, I want to compute something. I want to compute square roots. I want to compute, I want to make do addition, whatever. You might have thought that every different thing you want to compute, you got to go to the computer store and buy a new computer. You'd have to buy a new piece of hardware to do each different computation you want to do. So originally, it first arose in a footnote to Gödel's paper, effectively. That said, actually, that's not true. You can have a universal computer, which can be a single piece of hardware, which just by changing the program you feed into it, can compute anything you want. And so that idea, which sort of first really getting legs with Turing machines and so on, that idea has that idea has been pretty important in our world because it's what makes software possible. It's basically what makes most of modern technology possible. That idea for a long time wasn't widely accepted in physics. People always said, but physics is different. Physics works using equations and things that can't be described by Turing machines. That's been something, I was involved in the 80s and really pushing the idea that one should take computation seriously in things like physics. And now with this physics project, I think we have very good evidence for that. But so computational irreducibility is this phenomenon that you can have a process go on in nature, in physics, that is computationally as sophisticated as anything. It's like you say, well, I'm smarter than that physical system. I'm going to jump ahead. I'm going to have a smarter computer that's going to be able to work out what the physical system is going to do much more efficiently than the physical system does it itself. But actually, we know this phenomenon of computational irreducibility says that can't happen. And the sort of infinite time version of that is the undecidability of Gödel. That is, if you say, what will happen in this physical system eventually? Will it ever do such and such and such and such? Then that's not something you can answer in a finite way. And that's the original Gödel undecidability result applied to something more physics-like. In mathematics, you're building up these sort of chains based on, the axiom says I can go from here to here to here. That's what you're building up there. In physics, you're saying, I'm going to run this physical law. I'm going to run this rule for how physics behaves. What can happen? So that's kind of the analog there. Now, in terms of the comparison between mathematics and physics, in a sense, my project is an attempt to turn physics into mathematics. If my project succeeds, physics just became mathematics. If we have the underlying rule for the universe, then everything else, in principle, is just computable mathematically. Actually, I was Hilbert had these very famous problems that he defined in 1900. Problem number 6 is physics axiomatizable? So this is so we can think of our project. I don't think it's the most interesting view of it, but it is this question of, can we turn physics into a branch of mathematics? Now, this question of how do you tell whether something is a valid and worthwhile thing to be studying, I think Popper's definition is really very narrow. And I think it's good for throwing out a bunch of crazy stuff.
Yes.
But it's I mean, if you think about the great theories of our time, natural selection. Is natural selection falsifiable? Not really.
Mm-hmm.
Is the second law of thermodynamics? That's another big one, which I happen to have worked on a whole bunch.
Mm-hmm.
That's another one with a pretty complicated epistemological story.
Mm-hmm.
This thing of mine called the principle of computational equivalence, which is what leads to computational irreducibility and so on. Again, it is complicated to say what kind of a thing it is. That is, see, Darwin, for example, believed that natural selection was a mathematical law. It's not really true.
No.
It's a fact about, in a sense, it's a fact about the world. It's something to do with a sort of definition of how biology works. Mm-hmm. Same with the second law of thermodynamics, same with my principle of computational equivalence. You can have a version of it where you could mathematically prove it's false, but you might have set up slightly the wrong thing to be, you could prove natural selection is false by setting up some sufficiently idealized model of how organisms work. But that wouldn't be useful because it's not, it's a thing that's trying to describe the world. But I think so there's a little bit of complexity there around, what's important about these principles, like natural selection, like second law of thermodynamics, like my principle of computational equivalence, is they provide ways to think about things, and they're very powerful ways to think about things. They provide a way for us to essentially turn what we see in the world into a narrative that's useful to us. Mm. Now, having said that, for example, in this physics theory of mine now, one of the really cool things is how it dovetails with existing, essentially, mathematical physics. Now, is it to say that something is falsifiable, to say that it aligns itself with some physical law that, or some physical principle that we've understood? I don't think that's quite the falsifiability story. That's a different story. That's a story of some sort of aesthetic completeness or something. Now, you can ask the question, are there things we could discover that would make this theory of mine false? Well, there is one. If we discovered that the universe is a hypercomputer, that the universe can compute more than a Turing machine can compute, then we would prove the theory false. Mm. Unfortunately, there's a small glitch there, which is that we humans, everything we do when we represent things kind of symbolically, we have no way to communicate with that hypercomputer. So in a sense, even if the universe was a hypercomputer, well, actually in my theory, there would be a cosmological singularity, cosmological event horizon that would separate the hypercomputer from the rest of the universe. So it might be there, but we would never be able to communicate with it. And even if we mm-hmm. said, but that's an example of falsifiability. I mean, it's also the case this physics theory has a bunch of really, really fun predictions. I mean, it predicts the predictions are a little bit hard to say with total clarity because we don't know some scales that occur. So, for example, mm-hmm. there's a speed of light that, we know about the speed of light. It's the maximum speed that things can propagate through physical space. Mm-hmm. In this theory, there is an analog of physical space that we call branchial space of branching structures that represents basically the space of quantum states. And just like there's a speed of light in physical space, there's also a maximum speed in branchial space, which corresponds to a maximum speed of quantum entanglement, corresponds to a maximum speed of quantum measurement. My best estimate right now for the magnitude of that, which is it's a bit of a flaky estimate, but the best estimate I have is about 10 to the 5 solar masses per second. So that means that the maximum, if you were a galaxy-sized, if you were a hypergalactic mm-hmm. intelligence, the maximum entanglement speed would be a big deal for you. Just like the speed of light would be a big deal if you were an intelligence spread out over even the surface of the Earth, perhaps.
Mm-hmm. Or the speed of sound is important for bats, or the speed of smell and diffusion equation is important for dogs. Right. Interesting.
But so, I mean, just to finish that thought, I mean, so this maximum entanglement speed, if we were to see black hole mergers between 10 to the 5 solar mass black holes, we should see effects from the max. If the scale is correct, we should see effects from that.
So this would be in principle observable with LIGO, or depending on the distance, right? Mm-hmm.
If we were lucky enough, I think we'd see it anywhere in the universe. If two galactic center black holes, merged, there just aren't a lot of galaxies.
That's right.
And not enough galaxies, not enough time.
That's right.
So But there's another thing which they're just a boatload of predictions. So there are a bunch of things. So another one has to do with photon correlations, photons orbiting a black hole. There is, I think, a prediction about the way that correlations should occur for photons orbiting a black hole. That probably you could also get from, you might also be able to get it from quantum field theory and general relativity, possibly. But it's, well, actually, maybe that isn't even true. It may be specific to this theory, because it requires a merger of relativity and quantum mechanics, which is what happens in this theory and what hasn't really happened anywhere else. So
and presumably thermodynamics would enter in as well with Hawking radiation at those same boundaries.
Well,
right?
actually, thermodynamics is more of an underpinning. I mean, thermodynamics. So the second law of thermodynamics for people, is basically this law, 1870s. It was originated that says things tend to get more random in the world. So if you have a bunch of gas molecules, you very carefully arrange them in some corner of your room, and then you just let things go, the gas molecules will end up randomly arranged around the room. And it's been very confusing to people. How can it be? Because those gas molecules, when they collide, you could always play the movie in reverse. And whatever the configuration of gas molecules was in the end, the gas molecules, it's as valid a sequence of collisions between gas molecules to say they go back and they end up being in the corner of the room as to play the movie forwards. So people have been quite confused about that. I think I kind of figured that out in the 1990s, actually. And it's kind of, nobody seemed to care at the time. And it's been interesting with this physics project now, the number of questions about thermodynamics is quite large. So I'm really happy, because it was a thing that I was interested in when I was a kid. I finally figured it out in the 1990s. And the story is this. Basically, when those gas molecules are diffusing out, they make something that seems random to us. The reason we can't invert it is essentially the same reason we can't break encryption. What's happening is there's been this irreducible computational process that has essentially encrypted the initial conditions. The initial conditions are still there, but they've been encrypted. And the thing is that we as observers making our measurements, doing, figuring out how many gas molecules there are here and there, those measurements are not computationally sophisticated enough to be able to do the decryption. And so that's the reason that it appears that things have become more random. Even though if we looked at a microscopic scale and we decrypted what had happened, we would be able to say, aha, that came from something very simple. We can't actually do that. And that same phenomenon happens. So in this physics theory, when you do in general relativity and the theory of gravity, you're interested in essentially the way that observers in the universe can kind of piece together different parts of the universe. What's acceleration? What's a gravitational field? And so on. It turns out okay, so here's a little thing for you. This is particularly the work of young fellow who's been working with me, Jonathan Gorard, that the thing called the cosmic censorship hypothesis, which you're probably familiar with at least, is directly follows from essentially computational irreducibility arguments, and that follows in the same way that the second law of thermodynamics follows, that because you can't have an observer who sort of carefully sculpts their reference frame, that's why you end up having things like the cosmic censorship hypothesis. So, and I mean, it's a rather technical thing that some of these issues about Hawking radiation, that actually, I think our resolution of the black hole information paradox, it makes some implicit use of computational irreducibility, but it's not quite front and center. I mean, what happens, one of the mysteries about black holes is you can start off with this pure quantum state. It's all, it's all perfectly quantum mechanical. Then the black hole forms, and then you're starting to get this Hawking radiation, which is this very thermal, breaking the laws of quantum mechanics type thing. But then in the end, the black hole all evaporates, and you think, well, I'm back to my original perfect quantum state. And how did that work? Well, in our theory, we actually have a way to understand how that works. It turns out that there's an event horizon, which, anything that goes past the event horizon never gets to come back out again. But there's another event horizon. The event horizon, the usual event horizon, is associated with essentially an escape velocity more than the speed of light. But there's another horizon that is not in physical space, but in branchial space, which we call the entanglement horizon, which is a horizon where this 10 to the 5 solar mass per second thing comes in, and you can't escape from the entanglement horizon. And so things get trapped between the event horizon, the causal event horizon, and the entanglement horizon. And that's where we think, actually, just this afternoon, we were doing, because we're doing this crazy thing of live streaming a bunch of our internal science discussions. And we were just doing one this afternoon where I was realizing that something I thought I understood about black holes, I was wrong about, but where we actually can, where we were getting towards being able to have an absolutely explicit picture of how this phenomenon works, of quantum degrees of freedom being trapped inside the entanglement.
This purgatory between the entanglement, the classical or the event horizon, and now this new branching horizon, this sort of a purgatory regime between those two. I see. Okay, and that is you're conjecturing that is sort of the associative a nexus of where Hawking radiation phenomena would take place. Virtual particle, antiparticle. Interesting. So when you're, I mean, this is sort of reminding me of this classic, discussion, which I don't want to have about, whether or not mathematics is discovered or invented. But it does seem like, and in particular, because you gave some hints about this in your book, Adventures of a Computational Explorer, and you started talking about where you were going, and sort of the cover depicts this landscape of discoveries, but it's not only discoveries, it's also inventions. Obviously, in the case for Wolfram, it's literally technology that's being invented, so actual devices and machines that can do actual work in the computational landscape. I want to ask, when do you start to get this when you start to get the inkling that you're onto a discovery or invention, something that's new? I wanted to just harken back to your book, Adventures of a Computational Explorer, and you talk about the feeling, the alien feeling that you have when you are coming upon something that is new, or something that had been known before. Like in this case, you're talking about general relativity, and you say special and general relativity are things that physicists normally assume are built into the theories right from the beginning, almost as axioms, or at least in the case of string theory as consistency conditions. The idea that they could emerge from something more fundamental is pretty alien. And I don't know if you're paying attention to how much reaction that the Physics Project is getting online and the blogosphere and on Reddit and all sorts of places, Twitter, etc. But I feel that there is sort of this back reaction that's occurring, literally, where people are finding it so alien that they almost are shutting down. I mean, I've heard, friends of mine who are some of the most eminent physicists in the world, basically saying things like, well, I'll believe it when it's in a top-ranked journal, and we'll talk about that and how things are going with the actual logistics of publication, et cetera. But this is sort of new, and its novelty is enhanced all the more by the way that you sort of have chosen to release it, and how you've documented the kind of exploration log as you're going about it. You're doing this in real time, and you're doing this open source, and you're doing it in a way that is discoverable in principle by anybody. And I wonder, what is that? Is that disappointing to you? The kind of, I won't say hostility, but I will say, people are very skeptical, and it's not like, as I point out, it's not like I'm a living example of peer review not being a panacea for some of the things that I've managed to get by editors and referees, but it's still sort of the best tool that people think of scientists as manifesting. So, can you comment on that?
Yeah, look, I mean, the fact is that physics fields of science go through periods of rapid growth and periods of kind of slow, grinding, sort of hard slog for a century. Mm-hmm. Okay? And what you see, I've seen this probably in a dozen fields in my time, where there'll be typically a methodological advance, and then for maybe 5 or 10 years, there's a very rapid growth. The field may not exist before that time, or maybe like machine learning, where it had been stagnant for 50 years and then suddenly comes alive and lots of exciting things happen. Or back when I was working in particle physics in the late 1970s was another sort of period of rapid growth. And those are the dynamics of new fields or fields in rapid growth are very different from the dynamics of fields where they're in the cruise phase, so to speak. And so, I think when the physics that we have today, the two great theories of physics today quantum field theory and general relativity are both 100 years old. General relativity was 1915, quantum field theory, 1920s. And, I'm sure if I'd gone back and talked to, Albert Einstein or Werner Heisenberg or one of these kinds of people about the things we're doing today, they'd say, oh, okay, that's interesting. I'm not surprised, I know Einstein had even written things that said, I'm pretty sure space-time will end up being discrete, but we don't have the tools to understand how to work on this yet. So, he wouldn't be surprised. But you go 7 academic generations later, you go 100 years later, physics is not about, big changes now. Physics is about, it's a field that has achieved great things. I mean, there are different areas of physics, but when it comes to the sort of fundamental physics thing, it's really about, let's make an incremental change. And, fields have this character, and it's kind of, I've sort of been an entrepreneur both intellectually and commercially. It's a funny thing because when fields are young, they're very sort of, it's all very entrepreneurial, and people are, they're prepared to question the foundations and so on. When they get bigger, in order for the thing not to just completely self-destruct, it has to be institutionalized in some way. There has to be structure. There have to be, one of the things I've sometimes said is by the time there's a prize for something, it's too late for anything really original to be done. Right? By the time somebody has decided this thing is a field for which there's a prize, that field, is already mature. Yeah. And it's a little bit unfair, but there's something to that. I mean, I think that by the time there's a professional society, by the time there's lots of journals, by the time there's a department in a university, what's happened is there's a normal, there's a thing that is the normal way of making progress, and the system isn't set up to see something different. Actually, I almost have a good story to tell from just last night. I was my friend Paul Ginsburg who created this thing called Archive, which is a big preprint server that gets. I've never, because I worked on physics and wrote academic papers before Paul invented Archive. I've never used Archive, right? So I decided I'm going to upload this 450-page paper.
Yeah, we'll have a link to it.
Theory of physics to Archive. And, we uploaded it and it kind of got stuck. And it's like, I'm sending mail to Paul, why is this stuck? And he's like, well, because it's big and it's complicated and so on and so on and so on. And I'm like, I really want to be able to tell the story that anytime there's a paper that mentions fundamental theory of physics, you're blocking it from Archive. That's not true. So I can't tell that story. But in a sense, that story wouldn't be implausible because when has anybody made any serious claim that they have a big jump forward in finding a fundamental theory of physics?
Well, I actually get emails almost on a daily basis from people, shall we say, around the world who have, trying to convince me that there is a fundamental theory, that they've invented it, that Einstein was wrong. And, I always say it's surprising to me that they don't start off saying, Boltzmann was wrong or some other, lesser known celebrity than Einstein. But in fact, I mean, you're not saying he's wrong. You're saying he's right, but you're making not necessarily a prediction. In some sense, it seems like retrodictions are and Einstein did that as well. Einstein retrodicted the perihelion advance of Mercury, as we know, and that was early evidence for the veracity of his theory.
No, I mean, so there are predictions. We didn't even come to those, but there are a bunch of predictions. It's difficult because they don't have a scale. Einstein was lucky that his theory basically didn't need a scale, so he didn't have to say. I mean, he did need one scale, which was the cosmological constant. Yeah. And about that, he was plenty confused. But his theory, because of the nature of the theory, it doesn't have a scale. The same is true for my theory when it comes to phenomena that happen near black holes and things like that. But those are sort of special cases a little bit far away from what we're dealing with right now. There may be some predictions of the theory in quantum computing that, again, don't require knowing certain scales and so on. And strangely, there are also, there's a whole different story about applying the sort of mathematical raw material of the theory to areas like distributed computing and so on, which have a different kind of character to them. But I just coming back to sort of, I mean, I've got I get a huge number of these. I've got a theory of physics 2 type emails, I think it's kind of it's like many people write poetry and so on, and it's the poetry is interesting and meaningful to them. It may or may not have a profound,
Right.
global meaning.
It's earnest, but
right. It doesn't
Right.
mean. I think the thing that is surprising to me, and that is my main comment about these things is, we have, if we were going from just our everyday experience to a fundamental theory of physics, it's hopeless. I mean, there's a couple of thousand years of development, particularly the last 300 years of pretty intense development of kind of synthesizing things we know about the world and turning them into things like Einstein's equations or things like the Feynman path integral and so on. Those are deep condensations of things we know about the world. So in a sense, if you're going to try and discover a fundamental theory of physics, you are making it unbelievably hard for yourself if you're not leveraging what was discovered in the 20th century, basically, in physics. And the thing, I have the strange feature that I learned all that stuff when I was a kid. And that's kind of a weird piece of kind of life trajectory. I was a big physics enthusiast. I started learning about physics when I was 10 or 11 years old, and I wrote my first paper, which I published in a peer-reviewed journal, no less, when I was 15. So I had learnt sort of the standard canon of 20th century physics quite well. I then went on to kind of work on things which in many ways I think are more fundamental than physics. I think sort of the computational universe is in a sense the universe of all possible universes. The physical universe is just one of those. So I view it as almost a step down to be working on sort of the physical universe now, although it's really interesting and really fun. But I think that the question of sort of what there's a good question of how do you make non-incremental progress? What's involved in making non-incremental progress in science? So when I used to be in the physics business way back when, I wrote lots of papers. I think my peak productivity period when I was about 18, 19 years old, I was writing a paper every 2 weeks. And it was easy because it was a field that was in such rapid growth that, and also I had a secret weapon, which was I was using computers to calculate things, which for some bizarre reason other people were not doing. But in any case, I could say when it came to like peer review and so on, I could just predict if the paper is incremental progress in something that's already well understood, it'll sail right through. If the paper actually has a new idea in it, forget it. It's and
right.
that's
it's too alien
of a structure that's been built to deal with a particular status quo. Now, for example, I've been, in a sense, a lot of what I do, building computational language, I've been doing something that in some ways is kind of insidious and people haven't yet noticed. And I'm wondering how many decades it's going to be before, even though I'm telling you here, it's how many decades it's going to be before people notice. I mean, I might comment on do people notice, the physics theory that I'm now talking about. I spent 100 pages talking about the precursors to this in this big book of mine, New Kind of Science.
Yes. And,
we sold maybe 400,000 copies of that book and millions of people have looked at it online. I gave some talk at TED that, where I don't know how many, 1 or 2 million people have watched it. And I talked about this theory of physics. In fact, somebody reminded me recently that in that TED talk, which was just about exactly 10 years ago, I said, I wonder whether let's see whether by the end of the decade we can actually, hold in our hand the theory of physics. Okay, so let's say 1 million, 2 million people watched that. It defined kind of the story that has turned into the physics project that I've now been doing, and yet basically nobody followed up. So it's multiple millions of people. And so I think it again relates to this thing I was talking about earlier about sort of the context of understanding things. You have to have, if it's sufficiently alien, it just doesn't resonate. It doesn't connect with things people know what to do with.
Right.
But I think in one of the things I was saying that a lot of what I do is designing computational language to sort of bridge this thing between humans thinking about things and computers doing things. And, I've tried to sort of make, in a sense, what I'm doing is something like when people invented mathematical notation 400 years ago or so now, they were inventing a way of describing mathematical thoughts that was easily transferable, in that case from person to person. What I'm trying to do is inventing a way of transferring computational thoughts, both person to person and person to computer. And once it's person to computer, the computer can take it away and do very powerful things with it.
Yeah.
But in a sense, that notation is a way of defining how people think about things. And the fact that, I've spent 30-something years of my life sort of trying to build this notation for how to think about things, what I can already see is, for example, in this physics project, some of the ways I've thought about things there. When I work, like this afternoon, I was working on quantum spin and the origins of quantum spin. And, I can perfectly well tell the way that I named the functions, the way that I defined the functions in this computational language, they affect how I'm thinking about things. So
yeah, getting back to our language. Yeah.
But so in a sense, you ask, what, I have been in the business of basically trying to define how people think about things, but not in the let me persuade you type mode, more in the let me give you a tool that I've tried to make as efficient as possible at extending what you might have thought about anyway, but give you a track for thinking about things.
Yeah.
That's kind of, people haven't noticed how important and powerful that is, because people who know like Wolfram language well, they can form thoughts in that language much more quickly than they could express them, talking in English or whatever else. And they're really thinking in that language. And that's a thing that's a very, it's a very powerful thing to be able to do, but it's also something where it's kind of a different, you're asking, it's a different way of kind of reaching people than the let me persuade you that my theory is right type.
Right. Yeah. I've often, thought to myself that the best way to read one of your more technical books, such as, The New Kind of Science, is to actually read your popularizations. For example, as a companion. So in chapter 2 of Adventures, you talk about, you have the following statement. You're talking about searching through this vast landscape to find the core phenomena, the root of the core phenomena from a perhaps deterministic underlying model. Then you say, what is the rule for our universe? And then you say, I don't know yet. Searching for it isn't easy. One tries a sequence of different possibilities. Then one runs each one. Then the question is, has one found our universe? Now, obviously, you wrote that just less than a year ago. And then you said, in a little bit later, you say, I certainly think it's interesting. Almost, and I believe that the answer now is yes, right? I mean, I think you would say, yes, you have found our universe within the physics project.
I found a class of things which includes our universe. I would say that we still have, what's left to be done. Okay, so here's one of the things that is both surprising and interesting. So this phenomenon of computational irreducibility that I keep on talking about, even though you know the rule, it's hard to know what its consequences are. That bites us big time in studying fundamental physics, because let's say we have the rule, we start running it. Okay, we've got the first 10 to the minus 200 seconds of the evolution of the universe. Okay, what about the next 14 billion years?
Right.
We have to go and we don't have a way to get there. Now, the big surprise in this project of the last few months has been that a lot of facts about the universe are not computationally irreducible. A lot of facts about the universe are deducible by essentially mathematical type techniques, just knowing the class of rules that are used, not the specific rule. And that's a thing that, in retrospect, and it's typical for me at least, in retrospect, it's obvious. But it wasn't obvious for the last 30 years of my life. So what's obvious is the very fact that we humans are able to make sense of the world means that it's not computational irreducibility all the way up, so to speak. Because if it was computational irreducibility all the way up, anything that we would see in the universe, we'd say, I don't know why that's happening, because I have to be able to trace each little micro step down at the lowest level. But what we know is that there's actually great regularity in the universe that we can make use of. And that, in a sense, tells us there must be some layer of computational reducibility. And basically what we found is 20th century physics basically is the layer of computational reducibility that sits on top of what we now think of as this kind of irreducible substrate. And, so you ask about predictions. There are lots of interesting ones. As I say, it's slightly damaged by the fact that except when you're dealing with black holes and things, there are some scales that we don't know what values they have. We may figure that out even fairly quickly. There are ways I can imagine figuring that out. But, you talk about, you're talking about sort of the dynamics of the sociology of science. It's an interesting thing because, I've been involved in, starting some fields, and it's sort of fascinating that, like the whole area of sort of studying complexity for its own sake. Back in the 80s, I was I suppose I was a main standard bearer for a large part of that. And, I wrote the sort of the prospectuses, the manifestos for why that was a field that was worth studying. Okay, so I reckon that I made some mistakes in defining that field, which it's interesting the extent to which they've kind of bitten what's happened. I mean, the number one mistake that I made was not to define an analog of pure mathematics in that area. So what happens is you can have this idea, simple rules do complicated things. Now, the question is, do you study the simple rules for their own sake? Or do you only study them in the service of applications of those rules? And what happened in mathematics, which might not have happened, it's a historical accident in some ways that it happened, is that this field of pure mathematics developed that is studying mathematics for its own sake. And people might say, why do you do this? I mean, it's like, it's just, and people will say, oh, because it might be relevant. Some people will say, oh, because it might be relevant to technology. I don't think that's a totally convincing argument, or it might be relevant to science. The real reason is because mathematics managed to attach itself to education, and it meant that there was sort of a market for mathematically knowledgeable people that ultimately was driven by education. I mean, at the same time in history, logic, it used to be the case back in the Middle Ages and so on, mathematics and logic were neck and neck. They were both part of what people would learn. Well, notice that, everybody's obsessing about math education. Who's obsessing about logic education?
Logic. That's right. And that's the fundamental predicate for everything that mathematics is based on, right?
Well, yeah, so one can think that, but I think that what's interesting sociologically is mathematics managed to attach itself to sort of education. Logic didn't so much. Mm-hmm. And that led, among other things, to this internal market, basically, for pure mathematics. Mm-hmm. And in the area of complexity and so on, the internal market of just studying simple programs for their own sake didn't develop as much as it could have done. I mean, there's been 100,000 papers or something written on those kinds of things. Not like there hasn't been work done, but it isn't as big a thing as it should be, perhaps even will be, and could be. And I actually think the physics project will help in kind of emphasizing the importance of studying simple programs and what they do as an abstract, essentially mathematical-like thing. But the methodology is not like mathematics. Mm-hmm. I mean, it's also perhaps worth commenting on. It's been interesting to me to see. Because I was sort of, I think it's fair to say I was a sort of top of the line physics operative back when I was 20 years old or something, mm-hmm. And so I know a lot of people who were in physics at that time who are probably 20 years older than me or more. And unfortunately, many of them are not alive anymore, but those who are significantly older. And it's been interesting with the physics project. I've been sending email to all my old friends in physics, many of whom I've kept up with over the years, sort of saying, hey, there's this new thing. And it's amusing. I mean, the responses I get back are, it's a fascinating kind of sort of shell-shocky type response. It's like, that's not supposed to happen.
Right. Yeah. Right.
I mean, and to me, I mean, I didn't think it was going to happen either. I thought what was going to happen.
You didn't think you would discover it, or you didn't think they would react that way? Because I think
I didn't think they would react.
I see.
I thought that what would happen is that it was going to be I had an idea that I thought was a good direction, and I thought that the progress would be glacially slow. Mm-hmm. I did not think that we'd find out. I mean, the huge surprise is that we were able to figure out so much quite quickly. Mm-hmm. And I just, it's like we broke through this dam and it became quite easy. I mean, it's mm-hmm. kind of like, it's not supposed to be that way. I've never seen it in terms of sort of most of the work that I've done in science and technology is what one might call more synthetic, so to speak, as in you're building a computational language. You could do anything you want.
Yeah, it's evolutionary,
right? To make it useful. In my work in New Kind of Science, for example, and studying the computational universe is so vast, you can go and explore some different directions in it. You try and figure out general principles and things, but it's not. Whereas physics has this feature that there's this one universe sitting in front of us, and, you know, how does it work? And I really didn't think we would find it nearly as easy to sort of understand a lot of things about it. And, you know, I think the things we've understood. So for example, you talk about people proving that Einstein was wrong or Einstein was right and so on. There is one way in which we sort of deviate from Einstein. Actually, not so much from Einstein, more from Minkowski, who was sort of a teacher and disciple of Einstein's, I guess. And, you know, one of the things that came out of what Einstein did with relativity was this idea of space-time, the idea that, you know, time and space are sort of the same kind of thing. And that really got cemented by the work that Minkowski did on the mathematics of space-time, very elegant work, which has been very important in the last century of physics. But from that idea came the notion that is absolutely burnt into essentially all physics that's done, which is time is the same kind of thing as space. You know, and you might say, well, gosh, you know, I can move in space, but I can't move in time in the same way. You know, to us as sort of intuitive humans, it's like, how can you say space and time are the same? Well, you come up with all these thought experiments of trains moving at the speed of light and so on, and you kind of convince yourself that space and time are kind of like the same thing, and you can kind of twist yourself to say, yeah, they really are. And mathematically, it works out beautifully to say that. But one of the features of this theory is time and space are not intrinsically the same thing. Time is kind of the inexorable operation of computation, and space is a feature of this hypergraph that represents the sort of extent of the universe.
And time is discretized.
They're both discretized. I mean,
Yes.
they're all discrete setups. But the thing that, so you might say, gosh, you're doomed. You know, you'll never get relativity. But it isn't true. You get relativity very easily as a consequence of kind of the large scale behavior of a system like that. And so, you know, that was a place where basically it's actually historically interesting. I think I'm pretty sure it was a wrong turn in the history of physics. I'm pretty sure that if I look back at the early days of relativity and quantum mechanics, to me that's the only obvious wrong turn. I mean, the other sort of pseudo wrong turn is quantum mechanics, where people said, you know, my friend Dick Feynman always used to say, nobody understands quantum mechanics.
Right.
Okay. And I think he was right. I mean, I knew how to calculate all kinds of things in quantum mechanics. You know, you can crank up the mathematical formalism. You can calculate all kinds of things. You can calculate to, you know, what is it, 8, 9 decimal places or something.
Even more.
Amazing.
Yeah.
But it's like, why does this work? What's really going on? We didn't know. Right. And now we actually have an idea how it works. And it's really quite wonderful. And it's the thing that to me is just like absolutely spectacular is what Einstein's equations, which describe gravity and space-time, turn out the analog of those in this kind of branchial space of quantum states is basically Feynman's path integral. And that to me is just like, you know, these are two sort of defining ideas of 20th century physics, and they basically seem to be the same idea, but just applied in different settings. And that to me is really, I mean, for me, that's a real wow. And it's really something, I mean, I get very excited seeing that because it's just so beautiful that something like that could be the case. And in a sense, it you know, that's things like that. By the time you have enough things like that happening, you can worry about whether the telescopes will observe the first prediction that you get, but I don't really care about that.
Right. I think it's the faith that you need to have based on, you know, accuracy that's been demonstrated, right? And the efficiency. You know, I always say that, you know, echoing Dirac. Dirac used to say it's more important that your equations be beautiful than that they be right. I think you're sort of the opposite camp, but the beauty is emerging because it's sort of satisfying. Like nobody likes the idea that space and time are the same thing for the very reason you say. It's like I'm convinced nobody likes the idea that the Earth is actually spherical or nearly spherical. You know, it just doesn't comport with our cognitive biases, and yet it's true, right? And there's something even more beautiful about it being true. But it's violently opposed at first, at least. And I wonder if the consequence. Yeah, go ahead.
One thing to say about theories and falsifiability and so on, it's worth knowing a few stories to keep in your kind of, you know, your falsifiability, you know, quiver or something.
Yeah.
You know, Newton in his Principia, 1687.
Yeah.
Okay, he's got this big chapter about the moon, and he's trying to compute the motion of the moon. turns out it's pretty hard to compute the motion of the moon. He had the right theory, but it's pretty hard to compute. And he goes through this whole long chapter. Last sentence of the chapter is, but the apse of the moon is twice as great. So in other words, he did his whole calculation. He got an answer that was wrong by a factor of 2.
Right.
Now, did he then say, oh, forget it all, my theory of gravity must be wrong? He didn't, because there was so much other stuff that, and it took another 100 years for people to figure out, how that factor of 2 was, really worked out, and it was a difficult thing. So that was that's a sort of, the flip side of that is kind of what happened with Copernicus, where, there were Ptolemaic epicycles, and you could compute all kinds of things about planets, and it didn't really matter. Copernicus had a slightly different way of formulating things. I find it amusing. We in Wolfram language, we have to compute astronomical kinds of things, and like we did a big thing for the recent total eclipse that was visible from the US. Computing to the second using work from JPL and other places. When would the eclipse arrive? How do you actually compute it? Well, the answer is you use 10,000 epicycles. So in other words, even though Copernicus won, Ptolemy was wrong, in the end, the computation is done with epicycles.
Right.
So Copernicus was a case where the theory was, in a sense, at some level more correct, but the calculations were actually, he didn't even get as good results as Ptolemy got.
Right.
And
it wasn't
then, I have to tell a story. When I was in particle physics back in the 70s, one of the things I was involved in doing was making predictions from QCD, the theory of quarks and gluons, about what one would observe in experiments. Okay, so this one paper I wrote, I was calculated the rate of charm particle production, charm quark production. Okay? And, we got an answer. Well, it turns out there was an experiment that had been done that said the true answer is less than 5 times lower than the answer that we got. Okay? So it's like, what do you do? Okay, so the Popper falsifiability thing says, okay, throw away your paper, right? Well, I was sufficiently sure that QCD and my calculation were correct that I didn't do that. Sent out the paper. Now, admittedly, half the paper was, here's why this answer might be wrong, okay? But in the end, well, I wouldn't be telling the story if it wasn't for the fact that it ends with, and the experiment was wrong.
Right.
It was an experiment, and actually that experiment taught me an important thing, which is whenever I subsequently did theory based on an experiment, I would insist on actually visiting the experiment and going to look at the experiment and ask a bunch of questions. And it was really shocking to me how often, I remember one experiment, big particle accelerator experiment, I could observe this anomalous production of particles in some direction. And it's like, I'm looking at this thing and I'm doing sort of back of the envelope relativity calculations to figure out in the rest frame of this thing, where do the particles go and so on. It's like, you have claimed that you observe an excess of particles in a direction where there are no detectors. They're just, how can this be? It's a complicated story, and it's it's a big Monte Carlo simulation calculation to sort of back predict from what they'd seen. It was total nonsense.
Yeah, right.
But the thing is, experiments are hard.
Yeah.
And it's particularly, that first experience I had, it was kind of an experiment that observed nothing. And that's always very suspicious, because it's like they were looking for particle tracks in emulsions, and it's like, how long is the particle track? How good is your detector? How do you know if you didn't see anything? You observe nothing. Are you sure that's right?
Right.
Well, it wasn't right in that case.
Yeah.
But so I've kind of learnt that sort of theoretical triangulation is sometimes at least as important, if not more so, than the sort of the I dotting and T crossing of experiments. I mean, even in the case of general relativity and Einstein, I still don't quite understand what Eddington did in 1919. The story is Einstein predicted that when light goes around the sun, that it will be bent twice as much as previous theories had predicted. That there's essentially a gravitational magnetism as well as gravitational electrical force analogs.
What we call gravitational lensing, yes.
Yeah, right. But there's a factor of 2. There would be even Newtonian gravity.
Yeah, they
prediction, but it's a factor of 2 different in general relativity.
That's right.
So So,
which Einstein got wrong initially in his original calculation, which could have been borne out by an eclipse that occurred in 1914, but for the fact that there was World War I going on during the path of totality, it didn't take place. So serendipitously, it was good for Einstein because, as he later said, when asked what would have happened if he had been proven wrong, he said, "I would have felt sorry for the good Lord because my theory is correct." But he would have been starkly proven wrong, falsified, even had the events of World War II not taken place. That's right. And in fact, some doubt that Eddington was really capable of achieving the precision on glass plates, don't forget, kept in quarantine for 6 months between, where the stars are in the background of the solar field, between these two observations. You're absolutely right. It was not really confirmed with the accuracy that nowadays we astrophysicists would accept until radar astronomy in the 60s and 70s. And now, of course, we know it, to exquisite accuracy. It's one of the most highly tested features of relativity. Go ahead.
Yeah, no, I mean, it's always interesting to me that the intersection, for example, in the story of Eddington and Einstein and so on, I mean, the whole geopolitics of World War I ending and, German theory, English, verification, all this kind of thing. There was a complicated, in that case, even geopolitical backstory beyond just the sociology of a field's backstory.
That's right.
There was something even bigger than that going on there.
Yeah, I have a friend we interviewed on the podcast, Matt Stanley, who wrote a book called Einstein's War. It was interviewed on this podcast as well. So we'll link to that in the show notes. Yes, there's geopolitics, there's international intrigue, and kind of chauvinism, national chauvinism, and actually the fact that Eddington, being a Quaker, as Matt Stanley is, actually was one of the decisive attributes of why he was so pivotal in the story.
Right. I mean, I think that so by on those levels of issue, the response, it's fascinating to watch the response of new ideas in long established fields.
Yeah,
I would say my rating of this physics theory is it's going really well. It's been, I've seen other cases where you introduce something into a well-developed field and there's much more immune response.
Yeah.
I would say that what I'm seeing here is both in terms of established physicists, it's kind of fun because they're just not used to something like this.
No.
So they say, it's going to take me a while to digest this.
Mm-hmm.
And I'm slowly getting signs of digestion. Okay.
Right.
What does this mean in such and such a place in what you've written? So to me, that's a great sign. It means people are really reading stuff and so on.
Oh.
I think that we're also seeing lots of things like physics graduate students and so on who are like, I want to get involved. We're going to be doing a summer school this year to help people kind of get up to speed on this. We've actually done a summer school for the last 17 years about science and technology in general, but we're kind of adding a physics track this year specifically about the fundamental theory of physics.
Oh, great. We'll definitely put information in the show notes about that. That's a wonderful opportunity. Just to remind you of a famous Arthur Schopenhauer quote that all truth passes through three distinct phases. First, it is ridiculed. Secondly, it is violently opposed. And third, it is accepted as being self-evident. So may it be accepted so, because I know that you're after the truth and the truth indeed. I want to, sort of start to come in towards the airfield and conclude and respect your time. I want to, again.
I just want to add one thing about what you just said, because I think it's kind of interesting to people. So, when I wrote this big book, I have a big book. See this?
Yes.
Yeah, big book. It's a good. I usually keep it on the floor by my desk actually, because it's too big to go anywhere else. But the main point of that big book is that there's sort of a different way to think about the world that isn't in terms of kind of the mathematical equations that people like Newton and so on introduced back in the 1600s as a way to think about the world, but it's this thinking about the world in terms of rules and programs and computation and so on. Okay, so put this out there. And what was interesting, as I now realize, there are a lot of fields which accepted this quite quickly. Actually, the one field that had the most kind of pitchforkery, as I call it, was fundamental physics.
Yeah, physics, sure.
And physicists. But the thing that's been really interesting, it's 18 years since that book came out. And if you look at the history of modeling in science, okay, for if you said to somebody 25 years ago, said, how would you make a model of, I don't know, road traffic flow? How would you make a model of people searching the internet? How would you make a model of how, leaves grow on plants or something? They would say, well, I would think about an equation. I would write down this equation. I would define all these things mathematically, and I would try and solve the equation, et cetera, et cetera, et cetera. Okay? And that was the tradition for 300 years. Well, now if you ask those people how you're going to do it, and you look at the new models people are making of things, they are essentially all computational models. They're essentially all, we have a rule, we have a program, we run it, this is what it does, we can analyze it sometimes in terms of mathematics. And I think it's pretty frigging spectacular, actually, that after 300 years of what had been sort of, back when Newton was first introducing this stuff, there was a lot of fussing about it. How could you be discussing things purely mathematically? There's no way to reason your way through what happens. It's just mathematics. Philosophers were very upset about it, et cetera, et cetera, et cetera. But after 300 years, that's the orthodoxy.
Yeah.
And then last 15 years or so, well, it's all changed. But that's been a fascinating revolution because it's been quite silent. It's just happened.
Yeah.
And that was, I give myself a little bit of credit because if you read the preface to New Kind of Science, I basically said that was what was going to happen.
Yeah.
And and nowadays you ask people, how do you make a model of, I don't know, something about, epidemics or something? Well, there are the old-fashioned differential equation models. There are the new kind of agent-based networky type models. The new stuff, it's all kind of program-based models. And people just say, well, of course you do that.
Right.
And that's the transition. You talked about these phases. That's the thing that for the individual involved in the paradigm shift, so to speak, it's just really a weird thing because it's only 18 years ago that people were saying, it can't possibly be that way. Right. It's never going to work.
And now
it's all stupid. And then
I think
look around at the scientific literature and 100% of it is of the new models that are being produced, or practically 100% are working that way.
Right.
The one area which was not affected in this way of transition to kind of computational modeling was fundamental physics. Yeah. And that's a thing that basically we just changed last week.
Yeah. And I think, as I said, you are, by nature of the voluminous output that you produce and by nature of the fact that you work on such high stakes aspects of mathematics, of computation, and of physics, it's natural that you're going to be drawn. Controversy will come to you because of the stakes that are in play here. And I want to encourage people to read these books along with the popularizations, because I think it's impossible, at least in your case, to dissociate. People cannot not take you seriously because you've done objectively foundational work in all these different fields. I do want to, just because you mentioned this slow evolution, and then you mentioned, kind of these paradigm shifts. And I like to think of it almost like Stephen Jay Gould used to say, punctuated equilibria. Like we'll go through these phases and then something new will come along. And what irritates me is that there'll be people who will, decry the state of physics and say it's been stagnant for the last 40 years. And yet when something new and groundbreaking potentially comes along, they'll say, well, I don't understand it. It must not be right. And I'm not going to invest my time in it. But again, you cannot ignore it. Time will tell, certainly. But as you say, you wrote the New Kind of Science 18 years ago. I can't believe that because it seems like only yesterday.
It seems like yesterday.
My copy is
getting old.
Yeah, exactly. And I want to encourage people to read. For example, to look at Adventures of a Computational Explorer and see the things that what Stephen's talking about here and how they have borne fruit. And you, in fact, talk about not punctuated evolution, but you talk about these paradigm shifts. You say it's sort of a Copernican moment. We'll get to know just how special or not our universe is. Something I wonder is just how to think about whatever the answer turns out to be. It somehow reminds me of situations from earlier in the history of science. Newton figured out about the motion of planets, but could not imagine anything but a supernatural being first setting them in motion. Darwin figured out biological evolution, but couldn't imagine how the first living cell came to be. And I want to always point out that people say things about Darwin as this ultimately prescient person who had the most important theory of all of science. But again, he had his blunders too. He said things like, it is mere rubbish at present of thinking of the origin of life. One might as well think of the origin of matter. And of course, we know now a great deal about Big Bang nucleosynthesis. My late colleague Margaret Burbidge and the theory and with her colleagues on how stars produce nucleotides, and how we don't really appreciate things while we're in the midst of them. And I wonder, if what keeps you going is sort of this knowledge of history, as you've done a lot of episodes on the history of physics, not just through the lens of your particular vantage point, but I think from an objectively interesting standpoint of what these major breakthroughs were, and how, of course, the culmination that's inescapable is how this physics project might fit into that in the future history of this field, right, as it is written.
I think you mentioned Darwin, and I'm always I like history, right? So yeah. I'm always, one of the very fascinating mistakes that Darwin made, it's probably, I consider one of his most interesting mistake, is the last line of Origin of Species. So he says, I don't have it in front of me, so I won't get it precisely right. But he says basically, just as the Earth is going around the sun according to the fixed law of gravity, so new species, ever more complex, are being produced.
Forms.
So he thought, that's a very, very interesting idea. It turns out to be wrong, but it's a really interesting idea, that there is an inexorability to the production of complex species as a result of some force that he tried to work out, didn't succeed. One of his kids actually who became a mathematician, tried to help him do this, to figure out, is there sort of a mathematical theory of the way in which sort of what we now understand of as things like complexity and so on can arise. And he thought that, like the law of gravity tells us about the Earth going around the sun, that there might be a similar thing that would come out from natural selection. I think that this whole you're talking about people and their what happens when you're in the middle of paradigm shifts and so on. It's, I've been through a few of these. I mean, first point is, why do I do this stuff? Well, first, because I find it fun. Second, a thing that has really been an interesting dynamic for me in recent years particularly is, and it's really happening great with the physics project, is that I really like putting things out there that other people have a good time thinking about. In other words, it's, I don't really, it's not the satisfaction of, oh, I got it right. It's more the satisfaction of, I put this thing out there and people are having fun with it. I mean, it's kind of more like I suppose it makes me closer to, somebody in the entertainment business or something than I'm trying to nail it for the sake of having, I find it both internally for myself, I have my own sort of standards and definitions of success, and I don't really care what other people's are. And on the other hand, the thing that I really do get something out of is being able to give people, being able to sort of provide fulfillment for people. And I like to think that I do that in the kind of computational tools that I build. And I've been really pleased to see in this physics project that that's a dynamic that seems to have been picking up. And I think that the thing to understand about history, the two things that I've learned from studying history, which maybe aren't so obvious. One of them is, people say, 1905, Einstein introduces relativity. Everybody understood, relativity is easy to understand. It's a 5-page paper, which has basically no references. It's amazing it got through peer review. I don't know how that happened. I need to go find
his friend out. Was a peer. I think his friend was an editor.
Okay.
I'm blanking on his name, but yes, yeah.
Right. Mm-hmm. But I think that's usually the way it works. If you actually want to get it through peer review, is for a new idea, that is. But I think that the thing that the real story is, 1905, 1910, it took many, many, many years before people routinely accepted the theory of relativity as more than just this weird pseudo-philosophical, kind of pseudo-mathematical type thing. And, it's always, so first thing is, these things that you read in history books that say, such and such was discovered, boom, everything changed. Doesn't usually
paradigm shift, right? That's right.
It happens more with technology, actually, than it does with intellectual things. But that's the first thing. The second thing is, when you read in some place, so-and-so on this day figured out this grand idea, okay? That never happens either.
Right.
What happens is that you end up having to build up this intellectual context, and it takes years, decades sometimes. Once you've built up that context, then maybe there is some triggering event that happens very quickly. But without, there's always a story behind, all these things where it's like, so-and-so noticed this thing, and that was that was how they discovered whatever it is. It's never true. It's always so-and-so was thinking about this and working towards this and had an idea that was going to happen. Oh, and then they saw this particular thing, and then boom, a lot of stuff happened. And that's that's the experience from the inside, so to speak, is that it's glacially slow.
Yeah.
Both in terms of the response. I mean, the response in the world is always it's just charming to me, because it always works this way. At the beginning, I think you were quoting this sort of principle of how this works, but I think that's absolutely right. I mean, in the beginning, it's like, oh my gosh, can't possibly be this way, et cetera, et cetera, et cetera. And then eventually it's like, but it was totally obvious.
Yeah, that was
obvious. Of course
obvious.
it's that way.
Right.
How could it be any different?
Right.
I think that's, I mean, for the individual involved in initiating that, it's an interesting thing to watch. You have to be, I think for me, I've actually always had a certain degree of detachment from, which is not necessarily always, that's a challenging thing for ideas. To what extent do you just put the idea out there in the world? And to what extent do you package it? And to what extent do you push it?
Yeah.
Right? And so my point of view is, I put it out, I package it as best I can. I don't spend a lot of effort pushing it.
Yeah.
And packaging it means, for me, that means, do I write, do I try and make the thing accessible? Do I try and for me, that's super helpful for me too, because like I've been for this physics project, like last Friday, I did a kind of briefing for kids about the physics project, where I was trying to see, could I get the physics project to a middle school type level? And, I think I did okay, but I had a bunch of ideas actually while I was doing that, while I was talking about it, because I realized this is an easier way to explain this thing. And by golly, it helps me understand it.
Right.
And so that's, but by the time it's more kind of like the go convince people.
Right.
You
Yeah.
gotta convince this person.
Make it.
And the person says, but I've been doing physics this way all my life.
Right.
And it's like, well, I don't know.
That's
it's
right.
Like, whatever.
I think now it would be a new kind of marketing instead of a new kind of science. You need to
right.
really push it. I want to conclude with a couple of just because it's my prerogative as the host, and if you'll indulge me, I want to ask you a couple things. First of all, you were on Guy Kawasaki's podcast late last year, and he said something in the notes, to the audience that you may not have heard, but basically to the effect that you're the smartest person that he ever met. And I want to point out that one of the other people named Stephen that he knew was Steve Jobs, of course. And he related a story, where he had, sat in or just had talked to Steve Jobs right around the time that I believe Mathematica was sort of getting its name, and that Steve played a role in the creation of the name, although you came up with the name, but nevertheless, he convinced you of doing that. I want to talk about that, the creative mind, but also something that you share in common with him, in my opinion, which is your ability to motivate teams, and I saw that firsthand. We've known each other for 5 or 6 years now, but I've seen it with your team and the interactions that I've had with you, that you're exquisitely organized, you're very disciplined, but you have this camaraderie that you build up within the team that, as you describe in Adventures, as sort of, like a movie set, and when they wrap up, that you're compiling these projects. And I wonder, when you were working with Steve and sort of, were there lessons that you got from him? Obviously, it made its way into the next machines, and that eventually led to Tim Berners-Lee, creating arguably the World Wide Web on a machine that had Mathematica running.
Yeah, right. Funny story, right?
Yeah.
Footnote to history.
Yeah.
Footnote to history.
So how do you, as a leader, because you're also the CEO of a company and founder of it. How do you go about this process? We're going to have links to this wonderful blog post that you wrote about a year ago about kind of your life hacks and so forth. But with the typical thing for a mathematician, you say, how do you know if a mathematician is outgoing? They look at your shoes when they talk to you instead of their own. You don't have that. You're not shy, and you will have the ability to motivate people and to lead. And I wonder, where does that come from? Does that come from being a student of corporations, or how do you figure out how to be a leader? And what?
No, I think that the real thing with leadership, as far as I'm concerned, is to define a vision and be able to have something which you're excited about, communicate that excitement to a team, and it's also about caring about people and knowing something about people. I mean, I think I've been over the last 33 years that I've been building up my company, I've been fortunate enough to accumulate a lot of super talented people from around the world. Mm-hmm. And, I find people interesting, people, figuring out how does this type of talent fit into what we need to do at the company. When we build a new project, it's like a puzzle. Like, we've got all these talents, we've got all these projects we want to do. How do you fit them together? I mean, I think I think, as far as I'm concerned, it's a lot about, defining something. I think my responsibility as a manager is to make sure that people have something interesting to do, and to make sure it's something that they care about, that they feel fulfilled when they've achieved it. Those are things that I think are important. That's my responsibility, so to speak. Maybe their responsibility is to actually do the work to help make that happen. But my responsibility is, keep it interesting, keep it something that's really meaningful to the world, I hope, and to the people who are working on it. Mm-hmm. And I think, this point about, I happen to be interested in people. I think Steve Jobs he has very different, his and my style of managing people, I think, is rather different. His one feature of anybody who does hard projects, big projects that have never been done before, is they take a lot of just pure human pushing effort to make happen. And, what does that translate into? I think Steve's way of doing it may be slightly different from my way of doing it, but I think we both probably shared the fact that we could get really pretty pushy in trying to get projects to happen. I think the reason that happens, I finally understood. We've done many software releases, we've done many, big projects, and it's like, why is it that at the end, I said for a long time, there's never been, we have a team I've worked with for a long time doing big software releases. It's like, we've never had a calm release, a fully calm release. Why is that? Right? And then, having had that theory, we finally had one that was basically really very calm about a year ago. So to every theory, there's an exception. But really what happens is teams they work on their part, but when you're integrating the whole thing together to build the final thing, there always are pieces that weren't in anybody's silo, so to speak. And so somehow you have to push all these pieces together and sort of bridge those gaps. And that's one of the things that I think requires the most kind of sort of human pushiness. Mm-hmm. But I would say that for me, I happen to find people interesting. Mm-hmm. And I happen to, I think if I didn't, I would have gone crazy CEOing a company for more than half my life. Yeah. Because, it's, you always see weird things happen. There's always some weird pathological thing that happens. And it's like, oh, I've never seen that one before. But also, it's, I think I like to believe that I can work with a very wide range of different kinds of personalities, and that it's possible to figure out, for these different personalities with different skill sets, how can they fit into some overall vision that we have. And I find that interesting rather than frustrating. I think other people might find that frustrating. So, I think I for whatever reason, I kind of got two interests in life. One is in kind of drilling things down to sort of this reduction, this level of doing sort of intellectual, sort of clean thinking type stuff. And the other is people who are kind of almost the exact opposite of that. Right. Steve Jobs, one thing that I always liked about Steve, very clean thinking guy, very much a, what's the point? what's the point? What's the essential point? Not what's all the complicated, fluff around it, but what's the core essential point? And, I think that in a sense, a lot of, what I try to do in science and in technology is similarly sort of what's the point type thing. Mm-hmm. And it's, but not so much with people. I think that it's different and different interests.
Interesting. Yeah, I want to just close up with a couple more comments, questions about legacy, and this is again from Adventures of a Computational Explorer. You say lessons of the past in the chapter section called Lessons from the Past. A few years ago, I was visiting a museum and looking at little wooden models of life in ancient Egypt that had been buried with some king several millennia ago. How sad, I thought. They imagined that this would help them in the afterlife, but it didn't work. Instead, it just ended up in a museum. But then it struck me, no, it did work. This is their afterlife. And they successfully transmitted some essence of their life to a world far beyond their own. And it reminded me a little bit of a quote by Sam Harris, who is, you probably know, a very popular podcaster, author, neuroscientist. He has a chapter in his book called Waking Up, which is subtitled A Guide to Spirituality Without Religion. And he says, in a thought experiment from the philosopher Derek Parfit, I think that's how you pronounce the name, asks us to imagine a teleportation device that can beam a person from Earth to Mars. Rather than travel for many months on a spaceship, you only need to enter a small chamber close to home and push a button. All the information in your brain and body will be sent to a similar station on Mars where you'll be reassembled. Imagine that several of your friends have already traveled to Mars this way and they seem to be none the worse for it. They describe the experience as being one of instantaneous relocation. You push the green button and you find yourself standing on Mars, where your most recent memory is of pushing a green button on Earth and wondering if anything would happen. So you decide to do it. And it goes on a little bit. And he says, this has the benefit of leaving nothing to chance. The fact that before you get transported and teleported, they obliterate your original body. This has the benefit of leaving nothing to chance. If something goes wrong in the replication process, no harm has been done. However, it raises the following concern. What if your double, the clone of you, is beginning his day on Mars with all your memories, goals, and prejudices intact? You'll be standing in the teleportation chamber on Earth, just staring at the green button. Imagine a voice coming over the intercom to congratulate you for safely arriving at your destination. In a few minutes, you're told your Earth body will be smashed to atoms. How would this be any different than simply being killed? And I thought for a second, this kind of brings up this notion of legacy, right? Because if you can be teleported into a different place in space, how is that different in this thought experiment from how you get transmitted or teleported in time? And if, as you say, we can separate space and time, perhaps, in what ways could this take place? First of all, let me ask you, in terms of legacy, how do you define it? I'm defining it as teleporting my values into time throughout history and into the future, not so much in space. It doesn't interest me as much. There's a famous quote, I'd rather have one reader of my book 100 years from now than 100 readers of my book a year from now. And I think I'm curious, what do you see as your enduring legacy, perhaps, or what would you like it to be?
Oh, I don't know. I think that I'm, one of the features of the kind of science and philosophy that I think about is that I kind of slowly realize more about kind of the human condition and what the arc of in a sense, you could say, well, gosh, if you figure out the theory of the universe, then that's a thing that will sort of last for the lifetime of the universe. But that's not true. What you figured out is, for humans, here and now, this is how to understand how the universe works. It's all centered back on humans again. And I think that one of the things I've realized is that the permanence of anything one does, it's very much embedded within the context of some particular moment in history, so to speak. So it's not the case. I mean, one can have, it's kind of fun to imagine, so to speak, what will people think 500 years from now. But one of the thought experiments that I like to do is to ask, how has human purpose evolved over the last millennium, let's say? I walk on a treadmill for, a certain amount of time. How do I explain that to somebody from 1000 AD? It's like totally nuts. how will the people of the future, what will their value system be? How will it mesh with our value system today? Maybe there's something I've done that I think makes perfect sense that people will think is utterly shocking in 50 years. Maybe there's something that, is, these are difficult things to know. I think that, the whole question of sort of human permanence or impermanence, that's a whole different issue where, I suspect, one of these, it must be impossible stories is the whole human immortality story. And it's not impossible. It's just one of those things that has to be figured out. It's complicated. Mm-hmm. It's like if I've got a computer server, and it's been running for, a month, and then it crashes. It crashes because of some weird problem that happened, et cetera, et cetera, et cetera. That's kind of analogous to what happens with us humans. But we don't even understand it for computer servers, let alone understanding it for the more complicated case of our sort of molecular computing thing that's us. Mm-hmm. So I think, one of the things that is interesting to think about in your sort of, I would say it's a ship of Theseus. Yes. Derek Parfit's thing mm-hmm. is a kind of a version of the ship of Theseus transported another few millennia forward, so to speak. That was sort of an old philosophical kind of question of when you replace pieces of a ship, board by board, when is it the same ship? At what point does it stay to being the same ship or not?
If it's been completely replaced, right? Mm-hmm.
Right. So it's but I think it's an interesting thought experiment. Imagine immortality, either biological immortality or digital immortality. What does it then mean? What are your values if you can achieve digital immortality or biological immortality? I think digital immortality is probably the more extreme case because it has, for example, biological immortality still has issues like there's only one of you. Whereas digital immortality, that isn't the case at all. So what do you then, it's sort of an interesting question. Let's imagine, I think my version of this has been the box of a trillion souls. What if the future of humanity is a box of a digital, I think the very notion of a soul is actually kind of a fascinating projection from the distant past into this idea of computation. There's something about brains that isn't physical. What is it? Now we know it's basically computational. In the past, that was described as, the soul. So it's this box of a trillion digital souls. And, let's imagine that's the future of humanity. And that's where, some of us, at least in the future, end up. And then the question is, what is the value system at that point? What is the, you say, I want to have a legacy. And you say, well, okay, I'm plopping my legacy. I'm one of these people who records, every keystroke I type and all this kind of thing.
Wears cameras to conferences, right?
Yeah, that type of thing, right? So, and I certainly suspect that there's enough data kept about me that it isn't a big AI effort to reconstruct me from the data that's kept about me. Mm-hmm. And the question then is, okay, so what?
Yeah.
Then what I have to ask is, so there's the reconstructed me, or there's even the digitally uploaded me that's in this box of a trillion souls. What do I then care about? Mm. What thing do so I don't claim that I've resolved this question either for myself or for anybody else, but I think one of the things I find interesting about these sort of philosophical and conceptual questions is this. When, it's kind of like, for example, in the physics project, actually imagining that we might have a serious chance of finding the rule for the universe really gets one running in terms of thinking about the philosophy of it. When it's still off in the distance, it's one thing. But I think, I haven't really internalized the philosophy of digital uploading and so on. And I think, at some point it's a worthwhile thing to think about. And so the answer, I'm giving you a very long answer to a short question about, how do I feel about legacies of things? The answer is I don't really know how I feel yet, because I think that, we are at the first time in history when, here's one bizarre thing to think about, okay? We're at the first time in history where a lot of what's going on in the world is being recorded.
Yeah.
So we kind of know what happened. Now, if you look at a lot of human history, people say, what's the real point of life, the universe, and everything? a lot of what people look at is, works from antiquity that tried to define that, and that were written at a time when they were the first things on the block trying to define those things, and they had good things to say, and those things are probably still true because human nature doesn't change much. But people were looking to the past to know what's important and so on. They were looking to these, and so one of the questions is, when we look to the future, the box of a trillion souls, when we're free of all kinds of limited resources and all these kinds of things, one of the most bizarre things that I can imagine is people will say, oh, those guys at the beginning of the 21st century, we know exactly what they did and why they thought about things. They must, that is true humanity right there. That's what we have to go figure out, why they did what they did. Because now we don't have any of these constraints. We don't, where there is no sort of true humanity anymore because we don't have the constraints that they had at the beginning of the 21st century.
Very good. Yeah.
And, let's go look at all those podcast episodes and try and understand, let's try micro reconstruct, why did they do what they did? Because that is the true meaning. That's the thing that, in this question about sort of the translation of meaning, and there's no abstract version of meaning. Meaning comes from this sort of historical thread, and we are in the part of the historical thread where we're recording what we do, but we're not yet to the point where there are no constraints. So it's sort of we may have more responsibility than we think, so to speak.
Yeah.
About what the future of human history is, and I think that there will be pieces of that are big pieces that are I'll be like this idea of computational irreducibility that I've had. That idea is going to be very important for the future of human history. And you may not know that yet, but it's just like ideas like force and momentum that came out of the science of 300 years ago have been important in ways of thinking about things. I was amused last summer. I happened to be giving some testimony for the U.S. Senate, and it's the first time the word computational irreducibility made it into the congressional record.
Now it's permanently.
It tells one something about, in that particular case, it was a type of law that just can't possibly make sense.
Yes.
And this is going to happen more and more of understanding what can we understand, what can we not understand when we have the AIs. What is the constitution we set down for the AIs about what we want them to do and not do? How does it all work? That idea, like many of these things, I can tell you now, and you can go, check it out in however many years. Computational irreducibility it's already a reasonably known thing, but it will be a very well-known thing in time.
Yeah.
And in time, it will seem completely obvious.
Interesting. Yeah. And how revolutions in physics, which you wouldn't necessarily think would have theological or philosophical implications, just thinking about from Newtonian and kind of Aristotelian even, prime movers to Newtonian, angels keeping the universe from contracting in on itself, to obviously the quantum revolution and all those implications that come from a very analytic branch of human intellectual discourse, and yet make their way into these, sort of very weighty implications. And I wanted to finish up the discussion that we're having and schedule a future one, because I want to come back after the book comes out, and I want to get to that in a minute. But I want to finish up with three, kind of short answer questions.
Oh gosh, those are always the worst.
I know.
Well, a very good short answer.
One of them will be one of them will be very short because it's just standard. But this one may or may not be. I want to go the opposite direction. We talked about your legacy, which is legacy of us as human beings, as fathers, as people, teachers and educators, etc. I want to go the opposite direction. If you, so in my book, I have this wonderful quote from Søren Kierkegaard, who really sums up the astronomer's kind of dilemma, which is that his quote is that life can only be understood backwards, but it must be lived forwards. And I want to ask you in a brief way, what aspect of life was perplexing, mysterious, that was hard for you to understand? Admittedly, you were very precocious, 20-year-old with a PhD from Caltech, but as a 20-year-old, what was mystifying about life that now makes more sense to you? Perhaps now with the benefit of time has brought you some wisdom about it.
I don't know. I think look, I've slowly learned more and more about more and more kinds of things. I mean, I it's kind of I mean, one of the things that I sort of has been a fortunate thing in my life is just kept learning more stuff, and I have a decent memory. So, gradually after you've learned enough fields, learning a new one is more efficient, and you make all these cross connections. I think when I was 20 years old, I was doing physics, and that was all I was doing, and that was all I knew about. I didn't know about companies. I knew about computers as well, but I didn't know about all these different kinds of things. And so, that for me is the fact that I think if you'd asked me then, are these other things interesting? I would have said, no, I think physics is the most interesting thing. But turns out lots of stuff is interesting. I think my wife would, for example, say about me that, one feature that I have is I'm one of these people who has to figure out everything for themselves. So, nothing, and she's always giving me a hard time, that, 25 years ago, she told me something or other. And then I suddenly say, okay, now I'm going to do this. It's like, everybody knows you should do that.
That's right.
It took me 25 more years to figure it out. So
right.
it's I think that probably the wisdom of everybody else maybe was not, I've slowly learnt probably that, my default of is the wisdom of everybody else correct versus do I have to figure it out from first principles, maybe has changed slightly.
Interesting.
And I'm sorry, I need to go in just a moment here. So.
Okay, so I just want to finish up with a question I ask all my guests. That do you think that creativity, imagination, our center is named after Arthur C. Clarke Center for Human Imagination? Can creativity of the kind that you exemplify, can that be taught? Can it be something passed on from a mentor to a protege, or is it something that really is inborn, innate, intrinsic?
Don't entirely know. And I'm not through lack of data, so to speak. I mean, I think that I think a lot of people have intrinsic creativity. I think it is often squashed out of them by, for example, the educational system or by the expectations they think the world places on them. Yes. I mean, one of my kind of hobbies has been sort of trying to teach about computational thinking and other things to like middle school kids and younger and so on. And it's really fun and it's really interesting to me. I think the thing that is interesting at the middle schoolish age, it's really fun for me, like explaining things to kids of that age, because they don't have any fear of asking questions about all kinds of things. Later on, they're much more uptight. They're much more like, what are people going to think if I ask this question? Is it a good, whatever. So I think my working hypothesis would be that sort of everybody has a quite good degree of creativity. It's a question of whether they have the forcefulness, perhaps, confidence, or the things around them develop enough of that they can bash through and apply it. I mean, things I've done, like, this physics project of mine, this is, it took even me, and I've been involved in, big projects. I've done lots of things where people said couldn't possibly work, and I do it anyway, and it works out just great, and so on. I've had a lifetime building up confidence to do projects that are difficult and sort of, out of the mainstream. And even for me, this project took decades to have happen and almost didn't happen. So, I think it's my feeling is there's, the effort to get your creativity out. That's a big challenge. Yes. And can the world help people with that? They probably can. Can you add in creativity on top of somebody who's sort of had it squashed out of them? That I don't know. But, I think it's intrinsically there, and it's really the challenge is to just feel that you can express it and get the confidence to be able to do it.
Excellent. Okay, I want to thank you for your generosity of your time and your ideas and your thoughts. I'll put in a little bit of a plug zone. You can find Stephen on Twitter at Stephen_Wolfram. You can find WolframAlpha. You can find as many books. We'll link to them all, wolfram.com. And I just want to thank you so much for this wonderful conversation and chance to pick your brain. We'll get it out. Yeah, it was so much fun. Thank you so much, Stephen. Have a wonderful evening.
Thanks.
Bye.
Yep. See you. Bye-bye.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3,